1, 2, 3. Yeah, it's working.
1, 2, 3.
So many people. Yeah, let's wait maybe 2 minutes more. It's fewer people. It's a good friend. Okay, I think we can start. So good morning and welcome everyone. So I'm Nikolai Kolesnikov and Praveen. We work both at AWS. So today we're excited to talk about, I would not say excited, talk about Cassandra anti-patterns. So we have Cassandra and our agenda today. So we have the quick intro in Cassandra, common anti-patterns, use cases, case studies. So the case studies technically workarounds that I work for the customers. And finally, we will just end with the Q&A session. So we are sure many of you familiar with Cassandra. That's the Cassandra Summit, yeah. And what I can say, it's highly scalable, wide columnar storage. That's many of my customers using this on a daily basis for some reasons. So the first of all, it's no single point of failure. Zero downtime, that's what everyone wants. Peer-to-peer distributed architecture. So that allows you to read and write data from the same node. And this definitely adding resiliency with improving performance. So built to handle a massive amount of the data, probably a lot of you use this with terabytes or petabyte storage. Definitely works well. Cassandra's horizontal scaling and straightforward and cost-effective approach. So you can easily add more nodes to the cluster. If you want to improve performance, so it's linear scalability, it's great. So want to double, just double number of nodes. So, however, there are some common patterns that we usually observe across our customers that can cause performance issues. Today, we will explore 5 such anti-patterns, but the focus only 2. We don't have a lot of time to cover all of them. They may be quite complicated. So, are we going to talk about too many tables and large partitions, dive deep? So, but I will just touch a couple of them here. For example, probably you're familiar with the Spark usage. So if you have a large cluster and you're trying to, on daily basis, get the data out from Cassandra, read the data, slice and dice, aggregate, and prepare the report, sometimes node failing. So you can see that cluster is in down state, so 3-4 nodes died in some reason. So, but because the Spark, what it's doing, it's using the allow filtering. So it technically scattered gather your cluster to get data out. And it's already anti-pattern itself to get data out from the cluster, everything. So for this, there is a Cassandra enhancement proposal 28 that's called Reading and Writing Cassandra Data with Spark Ball Analytics that allows you to accessing Cassandra not from the front end directly from the 9042 port. You're going to use just direct access to access tables, and with the help of it's called the Cassandra sidecar to get data out and process it if at a high speed. Collections. So unfortunately, collections is limited. It's not limited. You probably can store up to 2 gigabytes there, but the performance drastically is going to degrade if you over 64 kilobytes. And it's reason because it can be sliced, it reads internally, entirely, and not be paginated internally. So there is a problem with collections. So keep them small. Now let's talk about the improvements that we can achieve with the fewer tables. So let's say in case if probably you're familiar with the situation when you have too many tables in your cluster and Cassandra clusters complain you created over 256 or 300 tables already. And from my experience, I see in the customers that even creating over 300,000 tables. So I would like to call upon my colleagues. So Praveen, stage is yours.
Yeah, thank you, Nikolai. And yeah, hey folks. So let's start diving a little deeper into more specific anti-patterns here. To understand what happens with your cluster when you have too many tables, let's take a deeper look into what exactly is happening on the Cassandra service. So for every table that you have created in your key space, it allocates roughly about a meg into your heap, JVM heap. So for example, if you have 1,000 tables in your Cassandra cluster, that's almost a gig of space in your heap that's gone to storing the table metadata. And this portion of your heap is actually scanned on every GC, but never released. So you're allocating a lot of space not very efficiently. And another bottleneck we see when it comes to having too many tables in your cluster is memtable flushing. So as we all know, every mutation in Cassandra is written to your commit log and then is stored in your mem table, which is in memory. Now, when you have multiple tables created, each table has roughly a mem table, which is in your heap by default. There are configurations to store it off heap, but by default, that's a configuration. The total space allocated in your heap for mem tables is shared across all tables. And what happens when you cross that threshold is it triggers a flush, which is a flush to disk. There are a couple of bottlenecks that hit there. There are only two flush writers, which are threads allocated for flushing your mem table to disk on Cassandra by default. You can expand it up to 8, but all tables share this bottleneck, which is a disk I/O operation, which, as we all know, it is very slow. And another bottleneck, what happens when we have too many tables in your cluster is we have many tables which have smaller mem tables, and by default, Cassandra tries to prioritize larger mem tables to be flushed to disk first. And when you have too many tables, we start fragmenting the space. So you start triggering premature flushes because you're meeting your threshold faster and we start triggering multiple disk operations wherein we are flushing smaller fragments of your mem tables because now we have too many tables in your cluster. Another regression that you see when you have too many tables in your cluster is increased pressure on your monitoring stack. And this isn't very Cassandra specific. It's a common design pattern, thing that we should take into account while designing any large-scale system, wherein you want to design your metric exporters and disk in such a way that your exporters are able to keep up with the metrics that are being emitted by your service. Cassandra emits quite a few metrics at the table level, and when you have too many of them, it starts imposing a lot of pressure on your monitoring stack. And when your metric exporters are not able to keep up with this, it starts leading to metrics being dropped on the floor, and in worst cases, it lets your service fly blind, which, as we all know it, operators hate that, right? There are a few other issues when you have too many tables. For example, client drivers during startup retrieve and download table schemas, and this increases your when you have too many tables, this increases your client startup time, right? There's also quite a few shared caches based on implementations, both server side and tables client side, which are shared across tables. So there's some impact on those as well. Now let's try to answer how many tables are too many tables, right? And this one is pretty hard one to answer deterministically because it depends on a lot of parameters, such as the Cassandra version you're running or the specific hardware you have and other configurations, right? But our load tests do give some pointers. So for example, this is one of our worst case load tests that we ran. We ran it against a 3-node 4.0.11 version of Cassandra. And we ran it on T2 XL EC2 machines. And we simulated a load test using Cassandra stress load test tool, which is packaged with your Cassandra binaries. And we simulated worst case traffic pattern where our traffic was majorly inserts. And the traffic was uniformly distributed across all tables in the cluster. So as you can see here, we see as we decrease the number of tables in the cluster, we see a linear improvement in write throughput. And much more significant win is our tail latencies. So we see significant improvement in P99.9 aggregated latency against the number of tables, right? And now let's go into how we can design our systems in a way where we can overcome this sort of anti-patterns, right? So one of the recommendations we have when we have like smaller or mid-sized workloads or migrations is to use NoSQL design patterns. One of the common patterns is to use a single table approach, wherein you overload your primary key or clustering key to represent different types of rows or different types of items within the same table. That reduces the total number of tables that you have in the system. Another approach, which is actually seen as an anti-pattern in SQL world, but in the NoSQL world, it's fine to do, is denormalization, where you introduce some data duplication, but you cut down on the number of tables in your system, right? A simple example is shown here, where we try to combine 2 tables into one, and we introduce some data duplication due to that. This sort of design pattern might be hard to put in place or conform when you have larger teams or multi-tenant systems. And then we have to start thinking a little bigger. So here we have an abstraction layer built for distributing your actual tables, which is abstracted. The physical location of these tables on the clusters is abstracted away from client side. So in this case, for example, we have a routing fleet that sits in front of different Cassandra clusters. For the client, it is abstracted away, and virtually everything looks like it's on the same key space. But physically, the tables are distributed across different clusters, and we have routing metadata to support this and help our routing fleet route the connections accordingly. This sort of architecture helps you scale horizontally because you can add and remove, scale in and scale out your Cassandra clusters in the backend, but completely abstract it away from the client side. However, it comes with a lot of challenges. For example, one challenge would be how you would aggregate system metadata tables for a key space which has tables distributed across different clusters. In those cases, maybe using managed solutions would be preferred. Now I'd like to hand it off to my colleague, Nikolai, to talk more about large partitions.
So, but before I'm going to jump to large partitions, I will add to the previous slide that we usually observed a lot of customers creating table in the case of engineers, let's say the experience with the MySQL database or any RDBMS system, and they're trying to replicate the same concept of the workload and recreate the same number of tables. Like if you have 110 entities, you'll go and just create 100 tables and expect that's going to work. Maybe on the initial stage when you have a little bit data, but after you will see that completely work differently. Thank you very much. Yeah. So let's talk about large partitions. From my experience, I would say like 80% of my customers that I'm working experiencing this issue with large partition. It's not, I'd say, a problem. It may be just the design thinking. So how you initially build your system, you probably don't test well initially, or you probably don't know even enough information about your data geometry. So how the data will look like in the future, how data will be distributed. And if it's small startups, they probably build something quickly, and after it will going to grow to something bigger, they will see this issue later. One example here, the customer is building a system, and there is just a primary key. They decided to use the customer organization ID. And for small customers, tenants, I would say tenants, they have, let's say, maybe private tenants, 10, 15 rows per partition. But after they onboard their, I would say, corporate clients, they're going to change the structure, but the number of transactions against this key is going to grow and grow very fast. And the problem is going not just to grow like whatever slow I would describe. I would give more proper word for here like a linearly grow or exponential grow. That's dangerous. So, and what we noticed there that sometimes customer, even they building a system and taking into account the large partitions, sometimes they use a select statement without clustering columns. So it immediately maps everything to the memory when you read and touch multiple SS tables from the storage. So that might be an issue too. So utilizing identical key that I already mentioned, yeah, they, for example, it's a customer ID or organization ID, something like that you can see in their table. It creates an issue immediately. So and moreover, it's affecting compaction process because it's taking more throughput to compact large partitions anyway. So, and you will see this is a parameter in Cassandra YAML file that's responsible for threshold here. So my experience suggests that maintaining partitions should be under 10 megabytes, don't go over. So 10 megabytes, it's a perfect solution here when you design. It definitely can help improve the performance of your cluster to a great extent. And you will be able to easily scale Cassandra without surprises. So, because it's usually a lot of surprises on the road. So, and additionally, so sometimes I see customers using like store some binary workload. The workload itself might be quite large. So let's say 10 megabytes, 15 megabytes, they store images inside, or they store some, like let's say some medical information that's usually might be quite large too. So and they're trying to at some point split, but split not enough that even 1 megabyte or 2 megabytes, and you don't know how many rows you're going to end in this partition. So partition can be easily over 500 megabytes. In my experience, I see the partition at 2 gigabytes. Close to 2 gigabytes. It's like extremely large, and the customers ask us to help to redesign complete solution and move to the new schema. So, and if you have a large payload, maybe sometimes to think about maybe it's not the right place to store this large payload in Cassandra. Think about something different. Maybe it will be memory solution that close to Cassandra, or it's some maybe object storage that you're going to choose to store the object, and store just a reference link to your object inside your table. So case study one.
Yeah.
Yeah. So so the for small customers, like mid-size clusters, when they have one application per cluster, we can easily just redesign it. So there's not a lot of efforts there. And usually you can find a low-hanging fruit there, especially in the regular columns you can bring to partition key, or sometimes you can look into and say, okay, in the clustering columns, if I move the clustering column directly to partition, it will improve some data distribution there, split the partitions on the smaller parts, and you can easily make an easy improvement without like hurting overall like infrastructure. So yeah. We can go next. So case study 2. So we have a customers that use Cassandra in a way where it's only one large cluster. So it's a shared cluster that a lot of applications there. So it's not only one or three, it may be 100 applications there. And they might affect each other because they just use large partitions there. Moreover, they just figure it out, okay, we create something, and we didn't know that actually is going to affect the overall performance, but at the late, it's affecting all your applications. All applications start slowing down because it's on one application, hurting everything. So one approach here is to build a unified data storage on top of Cassandra that allows you to store data in unified format. In this case, your primary key will look like unified, so it will be the same. It will be prefixed with a bucketing, like a bucket ID or something like that you can use, where each bucket technically might be stored in different clusters. So you have a fleet of different clusters where you can split these buckets and store them across different clusters. And I will just reuse the same architecture that previously mentioned by Praveen here. So by just adding additional bucket there. So the bucket store multiple partitions, but bucket should have a limit. So it's limit how many partitions it can store, at what size. In this case, the cluster should automatically split a new bucket, and your workflow can go directly from the fleet to proper cluster. Okay, we can go next. So let's conclude here. So my recommendations here and the Pravin's recommendation would be to keep the number of tables low. So keep them under 200, don't go over. So I think the most products that you can find right now, even its data stack server of its Cassandra, it's automatically complaining about that you exceeded the number of tables. And it still states if you read into 56, it complains, it gives you a warning, and after it just fails after 512. It will be failures. Use guardrails. It's a nice new feature in Cassandra 4 that you can find Cassandra 4.1. You can set the number of tables that you allow to create in the cluster. So it's a good way to manage the number of tables. And aim to keep this the same size of partition under like a 10 megabytes. Don't go over. And test your workload. So use the tools, so frameworks that are available. For example, out-of-the-box Cassandra stress tool, perfect tool. Even if people don't like this, I like it, and I continue to use it. So another available TLP stress test that's developed by the last Pickled. So another tool that you can use, NoSQL Bench. And sometimes I like to use the tool that's called Locust. I don't know if you're familiar with Locust. So the Locust is another test framework that allows you to imitate your like a real workload with HTTP requests. So it will look like you have real cluster that's attacking your Cassandra. See, that's how it's going. So and it's easy to write because it's just a plain Python. It's easy to deploy quickly, or you can use scale. So you can produce 1 million transactions per second there. So it uses distributed architecture too, to just create a workload. So for the large partitions, you can actually use node tool stats, table stats, to identify them, or you can use the virtual tables. In virtual tables, the statistics available. Just look there, so you will find your largest partition there for each table. Okay, thank you. If anyone has questions, we would be more to happy answer them. And afterwards, you can find us here. So, yeah. Has a question?
Yeah,
Yeah, we can hear you.
so you talked about like how having a large partition is a big anti-pattern, right?
I would not say anti-big pattern, but it's anti-pattern still.
Anti-pattern. So have you seen any use cases where a Cassandra table might have a lot of columns, say 3,000 to 5,000 columns, but in the end, the partition size isn't big. Let's say it stays on the 10 megabytes, but 5,000 columns, these columns are getting updated frequently or added to it. Would you consider that an anti-pattern?
I've seen this couple patterns that you mentioned right now. So what we usually recommend, we switch from to have a lot of your columns in a way that's horizontal, it's a separate column there, to maybe sometimes we compress the value inside. So we see that, for example, if they store a JSON or something like that, and change it from just like a row in a partition. Is that what I mean? So you have a column there, but now it's just a row with partition with specific column that says, this is like key value, like a key value pairs. And plus you can add the sharding value there so you can still split them. But the problem here, you need to keep on this splitting number. So when you're trying to read everything, so where the data should store, it should store on the application side. Application should not upfront. So this partition stores, let's say, 5 buckets. And we read it back, so it will read each bucket by one. Yeah. So that's, you can technically from this representation go like this in partition and split the partitions.
And so you usually recommend this change because the large columns you've seen performance issues with that?
So you might have a lot of columns, but if it's not affecting the size,
Of the partition?
yeah, so that will be fine.
So in the end, it is the partition size that'll be.
Yeah, the partition it will be available because I've seen like a 4,000 or 5,000 even columns, so a lot. And it's afterward just affecting the size of the partition. Yeah. So yeah, I will, before we wrap up, here's some other events coming up to we think you might be interested in. We have a workshop and AWS dinner there, so we have a booth in other sessions. So we look forward to seeing you there. Thank you very much.
I think we can take.
Yeah.
Right, so you say 10 megabytes, right? In most of our applications, store in one of the block columns.
Yeah.
So in this case, what kind of pattern would you
Store somewhere there, so you can have another storage, just a link. Your table will be just a ledger for your artifacts, but these large artifacts will store in different storage. For example, Redis can store up to 512 megabytes in memory. You can have the object, if performance is important part of you, like it should be milliseconds, you can store the object there, but the reference you will store in Cassandra, and you can quickly get the data out by the reference.
Yeah, Cassandra as more like a data pointer to
It's
where
like the main,
physical.
your main ledger, you store your data there, but the objects, large objects, it stores somewhere different place.
Yeah.
different table?
For example, Redis, it might be Redis. You actually,
In memory, right? So
yeah, it's a memory solution.
in Cassandra, I have created a table that has, let's say, 10 columns. One is a block, which is like a customer statement data that they compress and put it over there, right? So it's
You
not
can-
in memory, but it's, do you recommend putting in another table?
Yeah, I recommend you put in even
Because you cannot support joins, so they can
Yeah.
get it. They have to do it like a multi-fetch.
Multi-fetch pattern.
Yeah. So about multi-fetch pattern here, you can use, if you use Java, so the driver has a custom codex. You can develop your codex that behind the scene, you looks like you're querying the Cassandra table, but behind the scene, it takes the link and make a request to different storage and return data. You will see this, it return you back the normal result. But the data stored in different place, but you can mimic this behavior easily with DataStax's custom codex. It works well. I didn't test this for super large objects, like that's 100 megabytes. I tested this for 1 meg, 10 megs objects, and it perfectly works with the custom codec. That covers this, and usually developers don't see it, so they just use it as standard, like a select statement from table. You have a prepared statement, and it will return you the large object back, even if it's not inside Cassandra.
Right. So, yeah, I know this is not for this session, but with the Cassandra 5 SIA, so you won't need this kind of split table anymore. You can create an index and you can really do the join. Is that correct? Or?
So regarding to 5, I don't have a lot of information. So, but you can ask. The session will be probably next. Here's one other presenter from DataStax. They can probably answer this question regarding to if it's able to support. Yeah.
Regarding the white table and null table, which is better on Cassandra basically? Better for performance, giving large number of columns or large number of rows?
Because you can easily split when you have a partition, so you can split the partition. You can add a bucketing value, so prefix your every key. So let's say you have 1 million rows, and you're trying to store this 1 million rows inside the one partition. Not like this, not like in a horizontal way, like the columns. So in this case, you can define, so you store per partition 1,000, so you will assign a bucket, so that each bucket start 1,000 values. And you know upfront so how many buckets you have. So when you query, you will provide to your query, supply your query with the bucket ID to get data back. You know the data stored there. You can use hashing techniques, you can hashing algorithms to figure it out, the bucket ID. Because if you hash your primary key, it will give you anyway the number, the bucket that stores this data. And you will prefix and you get it. I would recommend to go in a way to store this inside the partition and split the partition.
Cool. Any other?
Yeah?
Okay.
One way to get around using too many tables in a cluster is to just break it up into multiple clusters.
Yeah.
Does that put pressure on the application using multiple sessions? Is that another strategy?
Yeah, it will put some pressure either on the client side, or you can push that pressure to your routing fleet if you have another abstraction layer, and you can do something more intelligent there based on the queries that you're doing to only set up connections only when needed, right? For example, maybe something that's aggregated across clusters needs to set up the connection. Otherwise, we can have the connection set up more focused. Right? So that'll, for the client side, it'll still look like a singular one, but you can abstract the complication out. Cool.
Okay, thank you very much.
Thank you. Yes.
Hello. So I think I have to start because I have a little bit too much to cover. So this talk was supposed to be a joint talk between me and Shailaja Kukuri from Intel, but she's not able to join us. Well, basically because Intel canceled the product that her work was aimed at. The talk is about memtable pluggability and the kind of memtables, alternate memtable implementations that we have in Cassandra 5. And let's start with why we want to do anything about memtables at all. The memtable is this very important piece of the Cassandra local storage. This is the first place where every piece of data goes to before being reorganized and written into SS tables. And it has a lot of work to do. It has to take data from the user. It has to organize it in a way that's suitable for retrieval. And finally, it has to prepare it for being flushed into an SS table. So it's also on the synchronous path of every write. So it has to acknowledge a write before the user knows that something can later be read by users. And in this examples, we have some writes happening, a read being done by user 3, and finally something being flushed on SS table. Why are memtables important? They're probably the most important thing for the performance of the database. On the first hand, the fact that it's on the synchronous path of every write means that it directly determines the write throughput, the peak write throughput when you're taking a lot of data in a short term. We do more processing of every write, but that happens in the background, so it doesn't really slow down your other processing until eventually things get saturated. And then the memtable also matters because the bigger the memtable is, the bigger we can make the level 0 SS tables. And these SS tables determine also the height of the compaction hierarchy, or how much work the compaction has to do for you to be able to read things as quickly as you want. And also another part why it's very important is that memtables are things that stay in memory. And in large part, this means that they stay on heap. And because they also stay on heap for a long time, they're not something that can be very easily handled by the garbage collector. And they have a lot of complexity inside them, which makes them hard to process. So to be able to do improvements on the memtables in Cassandra, we started, well, the best way to do something like this is to play with different implementations, try them out, compare them against each other. And the best way to do it is by supporting some kind of pluggability of implementations into Cassandra. And since Cassandra 4.1, we've been able to support pluggable memtable implementations. We have an interface that the memtable implementation needs to support. And once you do this, you're able to first define memtable configurations in the Cassandra YAML. Like in these examples here, there are skip list, sharded, and try configurations. You can choose one configuration to be your default for the database. And you can also decide to use a specific memtable implementation for specific tables. So it may be that some tables are not suitable for some types of data. And in that case, you can just choose the ones that you want for every table individually. We have, at the moment, 3 different implementations that are provided with Cassandra. The first one is the skip list memtable, which is basically the legacy memtable implementation in Cassandra. That's the one that we've been using since, I think, 3.0. And it's implemented as a concurrent skip list of partitions. And for every partition, we have a B tree that defines the map to individual rows within the partition. And we have even more B trees below that to find the actual individual cell. Something that's important about this is that while you can store the data for every cell off heap, all of these organizing structures, the B trees, the skip list, the multiple levels of B trees, and all of the B trees for each individual partition, they're all on heap. which forms a very complex structure. The second implementation we currently have, which was made as a kind of a proof of concept for the pluggability piece in 4.1, was this sharded skipless memtable. At one point, when we started trying out Cassandra with nodes that have lots and lots of cores, above 20, 40, 60, you start seeing that the memtable or the concurrent skip list becomes a bit of a bottleneck because it's contended, the writes start slowing each other down, and one of the ways you can improve on things like this is by sharding the memtable. And we implemented a simple solution which basically uses several independent skip lists instead of one. And this way you can take advantage of many more cores that you could with just a single concurrent skip list. So this one also supports a blocking mode where every time you write to a shard, it serializes the writes to individual shards. And in some cases, this can be beneficial because on one hand, it lets other pieces of the machinery like compaction have more ability to work. And on the other hand, it saves some memory because sometimes we may attempt to write something and then fail because the compare and swap didn't work. I'll give some examples how this is beneficial a little bit later. And the third one is the most important new addition, which is the try-memtable. This is coming with Cassandra 5. It's a very different implementation. So instead of using a skip list for the partition map, it uses a try, which is a different data structure. And it's aiming to solve quite a few of the problems of the legacy stable solution. And if you switch to it, you're expected to get a much better performance as well as garbage collection efficiency. Now let's talk a little bit more in depth about this new memtable and how it works. There's a key concept that these new memtables use, and it's called byte order. So if you think about the legacy memtables, and basically every typical solution for storing maps in any database, they're usually comparison-based, which means that you have your types, you have your function, which is able to compare two values in the same type, and your structures are based on comparing different values of the same type. And by this, you're building things like B trees, which every time you're making a decision, you're comparing two values and deciding which way to go. The problem with this is, on one hand, that because you need a comparison, you need to be able to give values to the comparing function. You have to have these values in forms which are comparable. You can't take just part of the value and compare it with a part of the value. It has to be the whole thing to be able to pass it to the function. So the keys can be short, like integers, but they also can be very long if you have strings or something like this. And it often happens that in keys, you would have repeated prefixes. If it's a string, which is a path to something, part of the string will repeat. If it's a multi-component key where you have several clustering columns, for example, you would often have many of the leading components being the same thing, and just the last component, for example, being different to point to the specific row. And if you're not taking care to form a type of hierarchy between the maps, you're going to be repeating a lot of the comparisons you do when you're walking this structure. So there's a balance here to make between repeating prefixes or adding code to the system to make it work a little bit better and save also on space. Another part about our implementation of the structures is that they're partly because of this problem with keys in comparable forms, all of these things have to be kept on heap with a lot of overhead. And this basically means that the on-heap size of a memtable is much larger, typically much larger than the data size which can be put off heap. And of course, that structure is very complex, having all the trees for the different levels of the maps. And when you do modifications to it, you have to you throw away some objects and you create new objects. And these objects are not immediately thrown away. They stay around for a long time. They get promoted to higher generations of the compaction, of the garbage collection hierarchy. So they're not easy at all for the garbage collector to reclaim. And this complicates the process of garbage collection. So what did we do about these two problems? The approach we took is based on byte comparable keys. So if you imagine, for example, that in a database we're not storing different types, but just strings as keys. If we're using just strings as keys, one can think of, one knows that for strings you have lexicographical comparison, which means that if you're trying to compare two strings, you can start from the beginning, and the first time you find a difference, you can immediately tell which one of the two strings is smaller, which means that if you're trying to find some place that splits between two strings, you can shorten it up to some prefix rather than having the whole string or the whole key, which is in itself can be an advantage, but it can also be used in structures that are specifically made for this kind of structure of the keys. And these are called tries. It's something that's been around for since the 60s, and it's something that's also generally been not used in databases until recently. So yeah, the key idea here is that we have a little bit better understanding of keys because we have this prefix decisions, which lets us have better efficiency. Well, the problem with Cassandra is that we have different types. We have more than just strings. We have also integers, we have floating points, we have big integers or even big decimals, which are not comparable directly as bytes. So what we can do to sort out this problem is to do a translation of the value into a byte comparable form. For some things, it's pretty easy. For example, if you take integers, they're not comparable directly because negative integers have their highest bit set to 1, and positive integers have their highest bit set to 0. So negative integers come after the positive integers if you directly compare them. But if you flip the top bit, then they start being byte comparable. You can do a very similar trick for floating points in the IEEE floating points. You flip the head bit, and also if it's a negative number, you flip all the other bits, and it works exactly as normal comparisons would. You can do that sort of translation for all of the types that Cassandra has, and also you can form translations of multiple components as a one flat single byte ordered sequence, which makes it easier for the code that's below in the core database to just ignore anything about the internal structure of the keys and just deal with this flat sequence of bytes. So the try-mem table, which we introduced with CEP19, is a implementation of such a data structure for the mem table. It uses key translation to take all of the partition keys into byte comparable sequences. Then it replaces simply the skip list on the highest level of the mem table hierarchy with a try. The reason why it's just the partition map is because this work is not yet completely done. So we have done only one step of the process. We're still getting huge advancements, huge improvements, but it's currently only replacing the partition map. It works very well for key value workloads at the moment because of that. Now, the try itself is something that we built internally because we needed some features that you couldn't really get anywhere. There are some, one of the main structures that people would use for something like this is something that came out of the adaptive radix tree paper from 2013. There are some implementations of that, but we needed a few additional features that they couldn't provide. For example, being able to read concurrently with data being written to the trie, which is really important for the performance of the database. We also did a few extra tricks to make it efficient, which I'm not going to go into detail because we don't have the time. And finally, because they're a single writer structure, which was much easier to write and much easier to make correct than fully concurrent structures, you have to shard the mem table into a few independent trees so that you can use more cores and do more parallel writes at the same time. What did we get out of this? One of the first things that we could see is that random accesses into the mem table are about twice faster, so 1.8 times faster. So in this test, we wrote 10 million entries for a quick micro benchmark. The time it took to write these 10 million benchmarks was about 2.5 times faster using the trie mem table rather than the skip list one. And querying them is, again, almost 2 times faster than the legacy mem table implementation. The other thing that's important is the size of the resulting structure. If you're using heap buffers for everything, you can see that it's a huge drop of the size of a significant drop of the size of the mem table from close to 6,000 to 4.5 or something like that gigabytes for the same amount of data. If you're putting the data off heap, both are again smaller because you can take a little bit more off heap and you need less overhead when your data is in these off heap objects rather than buffers. But you can see how small a part is off heap for the skip list mem table, and that almost doubles when you're switching to a trie mem table because now we can also put the trie off heap, which makes it there are two effects of this. One is that because the trigger for flushing is the amount of memory you have on heap, then you reduce the frequency of flushing. You store more data before you need to flush again, which is very helpful for the performance later. And if you look at longer-term performance, we did a few NoSQL tests filling a node with about 1 terabyte of data of very small, about 100 byte payloads. And you can see this here is just the first hour of the test, in which you can see that the burst or the peak write throughput of the same database, only replacing the mem table with a trie mem table, it can take almost twice as many writes per second. And this can be sustained for very long periods. In this case, the test ran for something like a day and a half, and the blue graph is the one using trie mem tables, and the orange one is the one using skip list. You can see that it maintains over twice better throughput throughout this test. The reason why this uses not open source Cassandra was because at the time we did this test, the other things necessary for this kind of performance weren't yet in open source Cassandra. They are now. You're going to see it in a minute. So some of the things that also are important that in addition to the throughput increase, we get latency reduction if you're doing fixed rate reads and writes. It's about 30%. You can also see that every time you're creating a new SS table on level 0, it's about 30% bigger, which means sometimes you may need one less level of the compaction hierarchy, which can be a significant improvement. And something that was really important for me personally is that we can definitely see a reduction in the total garbage collection time for this test or for any test we've actually done, on the order of more than twice. Now, something else I wanted to discuss is the effect of sharding and how whether sharding is a good thing or a bad thing, basically. Because if your data is well distributed, if you're in partition hashing, or the partitioner works well and is able to distribute everything in a good way, then sharding definitely helps. Even if you're using just a simple skip list, and even if you're using a blocking variation of the skip list, which can only do one write at a time to the skip list, your performance improves by something like 10 to 20% just by sharding the mem table. And the try-mem table is about twice better than the skip list in that case. But then, once you start introducing skew, things start to get better for the skip list mem table, until eventually, when you have every second write going to the same partition for this specific test, then the skip list is better than all the other solutions. That the plain concurrent skip list is better than all the other solutions. But for anything realistic, up to 20% even, you can see that the tries and the sharded solutions are doing at least as well. Now, this was the part of the talk which Intel was supposed to cover. They started about, what was it, 3 years ago or something, or maybe even more. They started work on making Cassandra work well for their persistent memory products. And what they initially wanted to do was to create a completely separate storage system for Cassandra. But it turns out that we can actually get exactly the same benefit by exactly the same end result by just using their thing as a mem table, which never flushes. So a mem table that never flushes is the same thing as a completely separate storage system. So in this graph here, there's a mem table, our mem table interface that we implemented for pluggability. You can use it on skipless mem table that flushes to disk from time to time, or in a try-mem table that flushes to disk from time to time. Or you can use a PMEM, persistent memory mem table, which never flushes and only stores the data in persistent memory. Because that memory is persistent, you also don't need any commit log, because we just start with what you had the next time you restart the machine. Yeah, this project is not merged into Cassandra mainline because the persistent memory products were discontinued, and they didn't see any point in continuing and finishing the work. But let me give some details about how this worked. The actual implementation was done using a direct implementation of the ideas of the art paper. They used the same byte order translation of the keys that I talked about a few slides ago. All of the data is in memory, so you're doing in-place updates, very similar how you would do it in a classical SQL database. And because their processing was single-threaded, it's sharded and always blocking. So unlike our solution, they couldn't read a piece of data while the same shard is being written to, which is a bit of a disadvantage. They didn't give me any performance numbers to share actual performance observed, but they were saying that they expected something between 2 and 6 times better performance than the normal mem tables when you expand them to a big enough size. One thing that's interesting about this is that the mem table pluggability interface in this case actually completely allows us to replace the storage engine of Cassandra. So we have a mem table. The mem table controls whether or not you're actually flushing when the database asks you to flush, and it doesn't trigger any flushing on its own because it doesn't fill up. It also controls whether or not you need a commit log, you need to write anything to the commit log or not. And Some of the other things that you need to do for it to work well with Cassandra, like streaming data from one node to another, you can do, I mean, you can get the concept of how this could be done much more easily if you think about it as just a mem table. When it's time to stream something, for example, you can give a range to the mem table and say, please dump this into an SS table so that you can then stream it over. And the other side can say, I don't want this in an SS table, I want to receive it directly to the mem table, and this works. So the next time anyone needs or wants to do a separate storage system, they can do it using this pluggability interface. And the last thing I wanted to talk about is work that's related to these mem tables, or basically to tries and to byte order. In Cassandra 5, we have two more pieces. One is the BTI SS table format, which is basically you take the same data format as the legacy SS table format, and you replace the primary index with something that's based on tries. And again, for the keys, we take their byte order translation. Because we already have the complete keys and the data, we don't need to store the full keys in the index. We just need to store some prefixes, which lets us point to the exact place where the key should be. So this can be much more compact than the previous indexes. It's much faster to read. Again, depending on what your workload is, it's typically about twice faster. Accessing a single SS table. Something that's really important and really nice about it is that there's no need to manage any key cache or any index summary if you're using this format, because it doesn't use it. The try the try is fast enough that if you add to it a key cache, it's going to slow things down. And the index summary, because the structure is very page-friendly, it can actually efficiently be cached in memory just by the page caching of the operating system. Another thing that's really important, we talked about rows per partition in the previous talk. This format can handle millions of rows. It doesn't have any problems with lots and lots of rows, because again, it uses the same kind of structure, which you can very quickly index into and find what you're looking for. You don't have to copy the structure to memory, which you would need to do the binary searches in the legacy structure. It's used exactly as it is on disk, and we've tested it out with millions of rows, and it works well. The other related work, you can call SAI also something that's based heavily on tries and byte order. It's not for everything that SAI does, but some of the types that it does are handled by the same tries implementation, both for mem tables and on disk, and byte order. Another thing I wanted to mention in this talk is that with Cassandra 5.0, we've opted to keep compatibility in the default configuration of Cassandra, which means that most of the things I'm talking about today, or any other people are going to talk about in the rest of the conference, most of them are turned off by default. And if you want to run your system or benchmark your system or just test it or start seeing what you could achieve from Cassandra, we didn't have a way to select all of these options. So we're going to be supplying a new configuration file called cassandralatest.yaml, which turns all these things on. Why is this important? One of the reasons you can see on the right side, the performance of writes is several times faster. And I mean, just because these improvements can make your life easier. So, yep, this was the end of my talk. Here are a few pointers to a few papers that talk about tries and byte order being used in databases. The first one is the ART paper, the so-called ART paper, Adaptive Radix Tree. I think I actually have a mistake here. I think they wrote it 3 as a with double E. The other one is another example of how you can use tries for indexes on disk. And the third one is the paper, which is around exactly this work that I discussed in this talk. I'm ready for questions. So. Thank you.
Regarding the sharding, so you share two different data structures with different number of shards in your configuration file, 16 and 32 here. So it's new how to use this, and it will be 32 because it's power of 2, or it's number of CPUs, or what is it?
Yeah, so the default value. Sorry. So the question is, yeah, the sharded structures have a parameter, which is the number of shards that you would want to use. By default, the number of shards, if you don't supply this parameter, is set to the number of CPU cores. That's often sufficient. But if you want to get the highest possible write performance, you maybe want to increase it a little bit. There are metrics that you can look at, and by JMX, as far as I remember, which tell you how much congestion you have, how much threads are waiting for another thread to free up to. And if you see that these are going up, you can increase the number of shards. Because it's a mem table, you can do it at any time, and it's going to take immediate effect practically. Yeah, Derek.
In your diagram there for the try, you had basically single byte stride, but does it use a fixed stride for the try, or can it use variable length stride essentially for that?
Yeah, it is a variable length try. I actually have slides for that, but I didn't.
It looked like they were single characters, so I wasn't
Yeah,
sure.
so the view on the try is a byte try. So you can do, you look at it as if all the transitions are bytes. Okay. Internal implementation can use multiple bytes. Okay. It can use, well, it's using fixed size blocks because that's easier to manage in terms of memory management. You can allocate and free something like this very easily. But it's also because the cache is very happy when you're using the same size of blocks, and these blocks are close to 32, 64, something like that, like the cache line. Yeah, and so in 32 bytes with 4-byte pointer, the widest you can go is 8. So in some cases, we would do 3-bit transitions. In some cases, if the point in the try is not branching that much, you would just list all the possible transitions into one block. In other cases where you just have a lot of single byte transitions going down the path, you just put up to 28 of them into the same block.
And are you doing your memory management yourself? When you say it's off heap, that could mean a couple different things.
It's the memory management of the blocks individually for the try, of the pointers and nodes of the try, is done by us. We're allocating blocks using JEmalloc most of the time for off heap. And you can do it on heap using just allocating a big on heap buffer as well. So that's, I mean, your off heap, your mem table option for the data storage also selects whether these are kept on heap or off heap. If you're selecting heap buffers, they will be on heap. If it's off heap anything, it will be taken out. Yes?
Thank you for the awesome details. One question is, I can totally understand how the in-memory try works really well.
Mm-hmm.
Are there situations when the on-disk try doesn't really work that well?
Have I seen situations where the on-disk try doesn't work that well? Honestly, I haven't. And this actually has been in production since DataStax 6, which is at least 5 years ago. and I haven't seen anyone complain. Yes?
Yeah, the churn stats you mentioned, are those exposed via no tool or virtual tables?
Which ones?
The stats on churning, for key churning.
By key churning, you mean?
Thread efficiency, yeah.
Thread efficiency. I think they're only available via JMX. I'm not sure on that. If there's an automatic way to get to JMX stats via virtual tables, you could get to them, but I don't know. Yes?
I was wondering what kind of data sets are the performance numbers
This is just key value. I mean, this version of the try mem table is only key value stores because it only replaces the partition map. In a few months, hopefully, we'll have a version that does more than this. And the main reason to do that is not to have more performance, but actually to get more of the structures off heap and out of the reach of the garbage collector. I think it was G1 for the tests. Yes? Ariel? So the question is whether we can have one huge mem table for everything, and that's something that actually I haven't seriously considered. And you hinted at the reason. It's because it's going to be much easier to drop the things that you've actually flushed onto disk. Ah. Mm-hmm. I think that's a few years away at least, though. It's not a bad idea in general. Yeah. Okay, if there are no further questions, thank you for being here.
I just saw a familiar face. I thought I'd say hi. I'm Stan. We met
Hello.
in
Yeah.
Halifax.
Yeah.
Yeah. Thanks for the great talk.
Thank you.
Give it a second or two and it'll
Sounds good.
pop. Big enough?
Yeah. Hi, everyone. Pleasure to be here. Nice to see all of you and many familiar faces. Yeah, that's really good that all of you are here. And my name is Alex, and today we're going to talk about the importance of transactional metadata and the avenues it's opening for Apache Cassandra. So before we begin, I just wanted to mention that I have several copies of Database and Journals book, and I'm going to giving them out for the people who are asking good questions. So I have 4 copies on me, and I have several more stashed. Yeah, Mick is, yeah. So yeah, they're going to be handed out. Anyways, let's begin. Let me first give you an overview of this talk, and we're going to start with and talk about the motivation, why we wanted to make the changes that we've made. Since the best way to plan the project is first to have clear requirements about what we want to achieve, let's set also clear requirements. And because I'm presenting to a technical audience, I'm quite certain many of you would be curious about the implementation details. And in fact, many of you are probably here exactly because of that. Okay, that was weird. Yeah, lastly, since transactional metadata has already landed in Cassandra trunk, we can also start talking about the avenues it has opened and the future steps and things that we have started working on. So let's first talk about how we came to the conclusion that we need to make the cluster metadata transactional. Around 2010, a new wave of NoSQL databases, mostly inspired by DynamoDB paper, have appeared, and all of them had several things in common. Having homogeneous nodes running on commodity hardware and implementing cluster metadata through Gossip was one of the features that they had in common, in fact. With Gossip, you can have huge clusters of nodes with spotty connectivity, and nodes will be collaborating probabilistically, propagating state throughout the cluster. In Cassandra, Gossip was used for disseminating many things, among which were schema and cluster metadata, which consists of membership and ownership information. Membership information identifies the presence of the node in the cluster, while ownership information identifies the target nodes for reads and writes. There is nothing wrong with disseminating cluster metadata through Gossip, since that's what it's best for. The things start getting tricky when we expect Gossip listeners to have a coherent view of this metadata and act as if this was the case. So Gossip has become a subsystem that used to react to membership and ownership changes announced by the nodes. And it was creating, among many other things, something which was called token metadata object. So anybody who worked with Cassandra for long enough probably knows about its existence. Token metadata is built from the information passed by the subscribers of the Gossip state changes, and it is invalidated whenever the ring version changes, which also means that it has to be rebuilt. Unfortunately, this was happening on the hotcode path, which we ultimately would like to avoid with the transactional cluster metadata project. Now, let's talk a little bit about the motivation. Most of the Cassandra clusters operated today contain only hundreds of nodes, which is a relatively small number compared to the number of participants in something like a mesh network or some Internet of Things setups where it might be impossible to live without Gossip or spanning trees or something like that. We believe it may be more efficient to use simple broadcast as a first line of distribution and natural cluster communication as a backup to disseminate information that is currently being distributed by Gossip in older version, which will make it simpler to reason about and lead to quicker time-bound convergence. let's talk through the process of the node bootstrap. So when the node comes up, it contacts seed nodes, which can give it the last snapshot of the membership and ownership information known to it. But unfortunately, we cannot know that there are, whether or not there are other nodes that are currently trying to make changes to the ownership of the range we're about to bootstrap. The most straightforward way to work around this problem is to introduce a delay so that other interested parties could make their intentions known. To reframe this a bit, shadow round and other delays you see mentioned on the slide here are necessary, since we cannot really grab a lock on the cluster instantly or quickly ensure there is no other node that will attempt to modify overlapping ranges concurrently to us. Another source of complication is that the current implementation, Gossip does not provide a way to ensure the strict ordering of these changes, which may lead to the out-of-order propagation of the concurrent events. Say if two nodes are bootstrapping simultaneously, coordinator A may observe node 1 joining before node 2 joins, and coordinator B may observe them joining in the opposite order. This also means that there can effectively be two disagreeing views of the ring. Of course, in practice, all of this is not super important and can be worked around, since operators are usually careful and make sure to only permit safe operations in the cluster. But unfortunately, even if we're willing to ignore these things, there are still things that we cannot easily solve with Gossip. I will give an example of a transient data loss issue later in my slides. And besides, because of the issues with automation software or human mistakes, there is still some room for error in the current implementation, which we cannot fully eliminate. So one of the things we've been discussing in the Cassandra community lately is a concept of token ownership. While an idea of hash ring and a consistent hashing seems to be good on the paper, there are still some things that aren't obvious at the first glance. First one is that it is using randomness in form of consistent hashing and load balancing for load balancing and distribution, and this does not guarantee optimal load, because unfortunately, even though your hash is providing uniform distribution, your data is not uniformly distributed. There are partitions that outweigh the others in terms of size and load, and there are 2 to the power of 64 tokens if you assume the Murmur 3 partitioner. And the space between these tokens is rather large, which means that there are still many chances for hotspots. vNodes, as you may know, were an attempt to address the granularity issue, and they did allow us to pick the multiple sources for streaming, but this has not completely eliminated the problem with load balancing. The ultimate goal of load balancing is to have a way to gradually and dynamically relocate the data. The second problem is that token ownership makes it such that node's position in the ring, alongside with the replication factor, dictates which ranges it is going to own, right, because of the ring. Which means that you cannot pick a subset of nodes for a specific range and relocate the data to them in order for them to own this data without doing token arithmetics, or relocate a range to a subset of nodes without having them owning the neighboring ranges as well. So I consider this a problem. It is also important for us to have a single point of reference. Any node joining the cluster should be able to quickly and easily find the latest membership of the ownership state and modify it without having to wait for other nodes to announce their potential actions. If you take a look at how, for instance, Paxos v2 is implemented in Cassandra, its payloads contain a list of participants, and because there is no other easy way to ensure that two nodes have exactly the same view of the ring, and we should make similar information available for every operation, even eventually consistent ones, and we can make it very compact. A single number identifying the ring epoch should be sufficient. Of course, this applies not just to Paxos, but eventually consistent operations just as well. And coordinators and replicas should agree about the view of the ring, and we should have mechanisms that allow lagging participants to quickly catch up to the latest epoch for the operation that is ongoing. And lastly, we would like the ring consistency for the duration of every operation, which means that a version of the ring available at the end of the read or write operation should be compatible with the responses that the coordinator has collected from the replicas. All of these things are required to maintain consistency levels honestly. We have, for instance, if we advertise the replication factor of 3, we effectively are making 2 promises. By the end of the quorum write, we will have at least 2 copies of data available, and that the quorum read that follows the quorum write will observe the effects of this write. And let us see under which conditions these assumptions or promises may not be held. So I'm gonna walk you through the example of the transient loss of the write during the bootstrap. Imagine a cluster with only 3 nodes with a replication factor of 3 and nodes A, B, and C present in the ring, and we would like to bootstrap the 4th node, which is X. And as you may know, in Cassandra, in order to bootstrap a node, you have to add it to the cluster at first as a pending node, right? So it's going to be receiving the writes, but will not serve any reads. So the reader still sees the node X as joining. Meanwhile, from the perspective of the writer, X has fully joined the ring, A is already excluded from the write set, and from its perspective, the placements for this write are going to be B, C, and X. And the result is the transient loss of the write during the bootstrap. So effectively, the reader is going to collect the nodes A and B, or may collect nodes A and B as its replica targets. And since it's quorum, it is sufficient for it to complete the operation. And the writer may collect C and X as their write targets. And since these quorums are non-overlapping, we have a transient loss of the write. And one of the problems is that reads and writes are not monotonic with the ring involvement, and there is no order guarantees between these two. And this may result into this problem that has existed in the system for a long while. Now, let's discuss other problems. So if you're in the community long enough, you may have heard about Cassandra 13004, which was a bug that was resulting from the schema disagreement in 2 nodes corrupting the data during the read. So essentially, read repair was corrupting the data in the SS table. However, even if the results are not as drastic, there are still problems that are difficult to resolve. So there could be racing create table statements, and like schema disagreements can be manifesting in many different ways. So let's now set up the requirements for what exactly we're trying to achieve. First, we would like to make sure that we remain honest about the consistency levels, even during the range movements. This is a non-negotiable correctness requirement. We would also like to have safe concurrent bootstraps. Multiple nodes should be able to join and leave the cluster. And you should have 0 knowledge about Cassandra internals to make this happen. Next, we would like nodes to find agreement about the state of the cluster metadata quickly and easily, ideally using natural internode traffic. So there should be no additional traffic introduced to the cluster. Lastly, we would like the metadata changes to be completely transparent for the user. Clients connected to the cluster should see absolutely nothing while range movements are in progress, not even a single unavailable or a timeout. That would be great. So let's talk a little bit about the implementation details. We have discussed 2 things already. So let's try to sort of incorporate them into the implementation. We will maintain compatibility with the tokens during the upgrade period, and for as long as you continue using old node tool commands. So everything remains 100% backwards compatible. After migrating to the cluster metadata, nodes, however, will own ranges and not tokens. Good news for Cassandra maintainers is that while doing that, we have also made sure to remove the range wraparounds. So all ranges are now from minimum token to the maximum token, so there is technically no ring anymore. It's just like flat line from the minimum possible token to maximum possible token. For now, we have decided to maintain full placement compatibility with the old token model, but the plan is to allow dynamic relocation, fully decoupling range ownership from token ownership. So these should be not interrelated in any way. This is technically possible even now, it's just not exposed to the operators just yet. Right now, token metadata changes are just recomputations triggered by the listeners of gossip state changes, meaning that in 5.0 and previous versions. Instead of this, we will now have explicit transformations that live in their own classes and explicitly describe what they're doing. So you will be able to inspect every change executed on the system in lots of detail. If we assume that cluster metadata is an atomic variable and say that we start with some empty state, we can formulate the change events as pure functions that take cluster metadata from one state to the next one. No side effects in any one of them whatsoever. Results will be computed on all the nodes in the same way, and there will be no way for two nodes to have divergent views of metadata if they have seen the same sequence of events, which they will. This also means that every cluster metadata can be uniquely identified by the epoch. Epochs are monotonically incremented and comparable. So any two participants can quickly and easily understand who has a higher epoch and has to catch up. To preserve the history, all of these transformations are going to be stored in the metadata changelog. Long operations such as bootstrap, decommission, move, replace are now able to survive the node crashes and are now safely resumable. The metadata changelog is also going to be strongly consistent. There is only one permitted order of the events, and there can be no other history. The log is stored on a dynamic subset of nodes, which are called a cluster metadata service, or CMS for short. This service can be consulted at any point in time to find out the latest state and make the modification to this state. The participants in the cluster metadata service are managed by the cluster metadata service itself without any user intervention, reacting to the changes in your cluster size and health of the metadata log owners. So you simply specify the replication factor for the cluster metadata service, and the rest is done for you. Newly joined nodes only have to know a single node in the cluster in order to discover the latest state of the metadata. So there is no concept of CMS nodes or it's going to be introduced to your scripts or setups. Since some operations have no visible trace in the for metadata, such as bootstrap that was rejected because there was another bootstrap ongoing already, so the ranges were locked, or a recreation of an existing table. The only events that actually make it to the log are ones that actually modify it. So your script, which creates, I don't know, a table, if it exists, will have no effects on the cluster metadata object because it's not going to grow it exponentially large if it's even running every single second. And we only preserve the things that actually make relevant changes to the metadata. The rest are just transparent and do not bump the epoch. And finally, metadata state is computed from the log, as I have already mentioned. Starting from the empty metadata state, we apply all the events in the order without any gaps, and we this way obtain the latest version of the metadata state. Since we plan to allow rather many operations for that can transform the metadata state in order of tens of thousands per day. We decided to use data structures that have structural sharing in memory to reduce the memory footprint, because if you have several copies of cluster metadata objects in memory, we would like it to be as small as possible. And finally, most of the time, new cluster metadata changes will have no influence on the ongoing operations. Computation is going to be done completely off-thread and will be made visible only when it is complete. So when we manifest the epoch, this is the first time the node is going to see it, experience it, and there will be no additional computation required for it. All metadata elements, including schema, are now versioned. Changes to one key space or table do not bump the epoch for other tables and key spaces, and placement information is also versioned. Epochs are changed only for the ranges that are actually affected by the operations. So if you have bootstrapped the node, it doesn't mean that entire state has to be recomputed and the state or the epoch for each and every range has to be bumped. So only the touched ranges are actually going to get their epochs bumped. Read and write requests now include relevant coordinator schema epoch and epoch when the range for which the current request is being performed was last modified. This means that nodes can quickly and efficiently check that their epochs match, and the lagging node can catch up to the relevant epoch. And best of all, none of this requires communication with the cluster metadata service. Nodes can simply exchange the relevant metadata mutation among themselves without involving CMS nodes. So there will be no extra load on these nodes either. Let's talk about maintaining the consistency levels and how we have achieved whatever I have mentioned before with the loss of the transient writes. And I will simply walk you through the same things in more visual form. So let's talk through how the node X is going to be bootstrapped with the transactional cluster metadata. We now again have the same setup. We have a 3-node cluster, replication factor of 3, and the node X is being bootstrapped into this cluster. And here, the first and foremost step, we have something that we call prepare join. And during this, the ranges that are owned by the neighboring replicas are split, and there are no other changes being made to the state of the cluster. So basically, we introduce the new token where the X is going to reside, but apart from that, we do not make any changes to the ring. The next one, we add X to the write set. So this is very similar to the introduction of the pending node in the previous model. And yeah, we essentially say that, okay, now the write set is for the given ranges is expanded by addition of the node X. So if in the previous case, the range from 0 to 100 had a write set of A and B, now it's also going to include X. For the next step, we had to introduce a concept of a progress barrier. It is serving as a way to ensure we maintain the promises about the consistency level, as we discussed before. We can summarize the need for it in 3 conjectures. First one is the bootstrapping node has to receive every single mutation, so every single write that has been made. In other words, streaming must wait for the event that adds the target node as a write replica to be acknowledged by the majority of replicas owning the range before we can start streaming. Second one is the streaming should start only after a writing starts to the pending node. So before that, so streaming has to be blocked and it has to wait until it knows that the majority of nodes has experienced this epoch, manifested it. And the third one, all possible read and write majorities of replicas, replica sets for both reads and writes, as I said, have to overlap. their majorities, right? And this is done by essentially computing the majorities for each and every steps in a way that is done. We have a special simulator for that, and you can check the Cassandra code for more details. Every subsequent event must wait for the previous event to be acknowledged by the majority of replicas owning the range before it can be submitted. So the progress barrier is essentially preventing the next operation to be executed before the previous one has been acknowledged and manifested by the majority of the existing replica set. The next step is something we called mid-join. And in this step, we simply replace the node that is losing the range with the node that is gaining the range in the read replica set without any touches to the write replica set. And the last step, we manifest fully the X as a complete and rightful owner of the token it has bootstrapped for. And in this case, you see that we have moved from basically introducing the node through all the steps, and now it serves as both read and write replica for the ranges it is going to own. So to summarize the bootstrap process, now we are bootstrapping using the ranges and not tokens. And in order to bootstrap, the node first has to contact one of the ranges, one of the nodes in the cluster, and this node is going to notify it who is the CMS. The CMS is given the latest information about all the epochs. The node is catching up to the latest epoch. Then it plans, splits ranges, starts streaming, and moves through all the necessary steps in order to get bootstrapped. Between every operation, we have a progress barrier that prevents the progress until the majority of the nodes have experienced the epoch that precedes the next one. And finally, we unlock the ranges, and the node is fully bootstrapped. Of course, you may be concerned about what is happening if you're losing the majority of the cluster metadata service nodes. It's not a problem. We have a series of scripts that allow you to quickly and easily recover from that. So essentially, you can introduce new nodes by forcing a, so to say, two-phase commit over the existing nodes. We expect this to never be used by anybody. We wrote it in order to, in a way, placate everybody that don't worry, if something really, really bad happens, you still have a way out. But we cannot really conceive a scenario where something like that can be necessary. And of course, we've done a lot of testing in order to make sure that this feature is as rock solid as possible. As you may know, Cassandra has a state-of-the-art simulator, and we've done hundreds of hours of simulation on the Cassandra simulator using the fast testing tool that we wrote, which is called Harry. We also wrote special simulator for quorum intersections in order to analyze and sort of like conclusively prove that there can be no way for us to collect non-intersecting majorities for the steps that are being executed. So as long as we comply to the protocol that is given by the progress barrier, then can be no transient data loss. And we have created a new sets of tests, which we call coordinator or replica tests. In this case, you are writing tests from the perspective of a single node. It is either a coordinator or a replica, and the rest of the state of the cluster is completely simulated. So you can simulate arbitrarily large or small clusters by essentially talking and writing the behavior of a single node. So this is very useful for testing the scenarios of like this transient data loss and recovery from it. Yeah, so we have written a bunch of tests for the TCM as well, and you can, of course, take a look at all of them in the Cassandra tree. And if you leave this presentation with just one word in your mind that is associated with the transactional cluster metadata, I would like you to keep the word elasticity in mind, right? I think that Cassandra has to become more elastic, right? Like more dynamic. And the things that transactional cluster metadata is making not only possible, but many of these things are actually becoming trivial, are the following. I don't want to read them from you. I'm personally most excited about the byte-ordered partitioner. And I have heard that, for instance, Branimir is also very excited, the person who presented right before me, because it very nicely plays together with the trie-based mem tables and SS tables. And it is going to serve as a better metadata for LWTs that are existing. And for Accord, you will be able to improve your control planes and many of the operations that have been previously painful and had to be watched by a team of trained Cassandra professionals now hopefully can be executed completely painlessly. So in order to recap and sort of summarize everything that we talked about today, so we talked about the motivation, like why we wanted to introduce the concept of transactional cluster metadata, and we discussed why we would like to stop using gossip for this subset of things. Of course, we still are going to be using gossip for things like load, failure detection, and some other transient information about the nodes, but it is not going to be used for cluster metadata anymore. And cluster metadata is going to be now transactional. We've discussed the requirements, what exactly we would like to achieve, and we set the goal for ourselves before we set out with the project. You can also read the document, the CEP, on the Cassandra Confluence or Apache Confluence, and we presented it to the community, and many folks have agreed that this is the way to go, and we would like to pursue that. Then we talked about the implementation, some of the details of the previous implementation, some of the details of the new one. So basically moving from the token model to range model, making the metadata changes strictly ordered and consistent. And we've talked about the future and the avenues that transactional cluster metadata is opening for us, and that's pretty much it. Thank you very much for coming to the presentation. I appreciate your attention, and of course, the books still await the persons who would like to ask a question, so go ahead and shoot. Yes, please.
Have you simulated concurrent changes with multiple nodes of a change set? See if that works well?
Yes. In addition to the two simulations that I have mentioned, we have a third simulation that I failed to mention, which is metadata change simulator. The metadata change simulator picks one of the possible operations given the setup of the cluster. So it first pre-generates an arbitrarily large cluster, and then just looks at the state of the cluster and thinks, okay, can I bootstrap the node in the cluster? Can I make one of the nodes leave? Can I make, move one of the tokens in the ring and so forth? Then it makes a decision that, okay, I would like to perform this operation. And it can also, on the next step, instead of continuing with the bootstrap, it can choose to, well, bootstrap one more node, or have one node bootstrapping, one node leaving, or one node leaving and the other one moving the token. So we definitely have simulated the concurrent operations. This has been a huge area of our focus in the very beginning, because we thought that if we cannot achieve that, then what are we doing at all? So we definitely did a lot of that, and yeah.
How do you expect this to affect something like a 100 or 1,000 node cold restart?
Yeah, so I will repeat this one because I think I haven't repeated the previous one. How do we expect the cold, this to affect the cold restarts? So I'm assuming that cold restarts is like rolling bounces whenever you need to restart every single node in the cluster. Is this? So once again, would you like to bring up a whole new data center with hundreds of nodes, and none of them have been a member of the cluster before that? Is this what you would like to achieve ultimately? Okay, so in this case, we have two scenarios. One scenario is first, you bring up some of the nodes that are going to be the cluster metadata service. You can bring up one node that is going to be CMS. That's the quickest and simplest scenario and easiest to achieve. I would personally probably do that. Then you just start all the other nodes and they start registering, and registering is as easy as simply submitting a single LWT or Paxos operation. It is very quick. It's currently 2 round trips because we are using Paxos v2. I expect maybe there will be some contention, but even for a 1,000 node cluster, like we actually simulated way more contended scenarios with Paxos v2. We have not simulated anything like that specifically with TCM in this case, but I don't expect any problems to be happening. And in the scenario when you don't have any data in the cluster, instead of using the multi-step operations that I have presented previously, you can save something that you can use something that we call unsafe join, which is a single operation, which means that everybody just joins and in one step. So they register, they join, and after that you have a 1,000 node cluster, and I expect it to be, I mean, essentially all of the time taking is going to be startup time. You will not even notice anything on top of that. So that's my take on that. Anybody else? Josh, sorry. Okay.
So when you're in the case where you're adding a node and it's past the right join phase, all the mutations have to be routed to it, and then that node dies, what are the implications for availability? Like if you're writing a quorum, for instance, but then you've got a window where the system is basically saying, unless a mutation hits this guy that's in transit, it doesn't work.
So that's a difference between the concept of a pending range, which means that you have to write to the majority of the previously existing nodes plus 1. We have changed it, and we essentially expand the replica set by 1, and the majority is going to be number of nodes divided by 2 plus 1, which means that for 3 nodes and 1 bootstrapping, we have 4 nodes. So the majority is, of course, 3 nodes, but it can be 3 existing nodes. It
doesn't require the new node to actually be available. So if you go to bootstrap a node and it detonates on fire, you're still good with the old quorum. You won't have any availability. Right?
So you're not good with your old quorum. You have expanded your quorum, and you will have to write to all of them effectively.
All the 3 behave themselves.
Yeah, in this case, you have absolutely no problem. You will, as you expanded the quorum, you will have to write to 3 nodes instead of just 2. You can quickly revert the operation, meaning that you can sort of like abort the bootstrap, and it's a very easy and quick operation. Yeah, so that's the answer. Yes, please, in the white t-shirt.
What is the upgrade path going to look like from existing gossip-based clusters to TCM-based clusters?
Okay, the question is, what is the upgrade path from the existing gossip clusters to TCM clusters? The process is as follows. You bring up all the nodes with the version that is aware about the existence of transactional cluster metadata, and you start the upgrade process by running a simple node tool command. I don't remember, it's initialize CMS or something like that. There is a documentation on the Cassandra website, of course, for that, or like in tree even. This command does the following. It ensures that every single participant in the cluster has the same gossip view of the ring, meaning that they have converged in terms of gossip, because otherwise what state can we base our transactional cluster metadata upon. So that's prerequisite. If you have some nodes that have corrupted view of the gossip, you can actually ignore them. You can manually inspect. Like in fact, during the upgrade, we print the diff for you, and we say that, okay, here is the disagreeing nodes, and here is where they disagree. And you can still say that, you know what, I think that these nodes are wrong. I don't know why, and I don't have time to figure it out. So let's just say that I like this gossip state that like main one sort of looks fine for me. So let's go ahead with this one. And after that, we are using a two-phase commit, which requires all the participants to respond during the first phase and say, yes, I promise you that I will upgrade to a single instance of a transactional cluster metadata, because if you accidentally launch two upgrades, then, well, we would like to prevent that. And we would like nobody to think about like how to avoid something like that. So we have to consult not the majority of nodes, but actually every single participant. This is the point of two-phase commit. And after all of them have promised, you go through the second step, and you essentially instantiate the first instance of transactional cluster metadata. And after that, everything goes on as previously, just not with gossip, but with TCM. There is a single limitation that during the upgrade process, you cannot, like the metadata is essentially locked. So you cannot bootstrap or decommission the nodes. But the word on the street is that like if you are upgrading, you better not have also like bootstraps while doing that, because there can be several things in flight that, yeah, it's just many people don't do that. So yeah, that's the only limitation. There is a way to downgrade as well. So you essentially say, okay, convert the transactional cluster metadata back to the gossip state. The gossip state is propagated, and you downgrade. But I don't really anticipate anybody needing this, barring the issues with something else in Cassandra. Yes, sorry? I'm really sorry. I understand what you're saying. I just don't hear the question. Could you phrase it in a form that could be like, what are you asking? Like, are you trying to achieve something, or you think that the way we've implemented it has some?
So what you have done is you've taken that metadata service outside, right? So it could potentially be used for a dynamically moving partition between tables to different nodes.
Yes, thank you. Okay, now I see. Of course, the transactional cluster metadata can be used in order to dynamically move individual partitions between nodes. This is absolutely true. The only reason we have not done that is for everybody in the community to be able to keep using their current tooling, Cassandra tooling, because I'm assuming that you have actually like concept of tokens in all of your scripts, right? There is absolutely nothing that is preventing you from saying that certain ranges are owned by like a single node, or even a single token is owned by a subset of nodes. You can even say that the replica set for a given, I don't know, token is not 3 but 5 or 7. Like anything goes, really. So from the perspective of transactional cluster metadata, everything is just like a range and a set of nodes that owns the range. So this is already implemented. The reason we have not exposed it is that we wanted everybody to have an opportunity to transition first to the the system where this is like everything is transactional, and after that we will start introducing new tooling that will allow dynamic repartitioning, different ways of load balance, reintroduce the binary ordered partitioner, which would mean also that you will be able to essentially have shards in Cassandra and so forth. So this is in the books. Everything for that is essentially implemented as a prerequisite, but like the features itself are still to be done. But this is planned. Yes, please. Should I answer this one, or we're good? Oh. Okay, we're 20 minutes behind, so we have to take this offline. So let me. So we have still four books available. Yeah, I see like one person, second person, and yeah, third person. Could you please come?
Okay. Good afternoon. Hopefully you have gotten some coffee so you can stay awake. My name is Lorena Poland. I'm a tech writer for DataStax. I'm also an Apache committer, one of the first non-coder committers that the Apache Cassandra project got. And I've spent about 11 years with Cassandra now. And I was supposed to talk about another topic, but I'm going to talk about unified compaction strategy. So this is compaction for all. Go to my next slide. There we go. I'll give just a really brief reminder of how compaction works in case I have anybody who hasn't had a lot of experience with that, why you would want to use unified compaction strategy. We'll talk a little bit of the innards of leveling and sharding and improvements that have been made with this compaction strategy. And finally, a comparison to legacy compaction strategies. So today, well, I better stick with my slides. So Cassandra has a pretty straightforward way that it deals with doing writes. It writes to a commit log so that if you have any interruption of service, you can read that commit log back and get any of the writes that might not have gotten written to memory or disk before the node went down. It also writes to a mem table, so that's a in-memory storage, which is a representation of the table that you're writing. And periodically, depending on hitting a threshold value, the mem table will flush to SS tables that are on disk. Those SS tables are immutable. That's a really big part of the story because you can't overwrite them. They don't get rewritten. You just get new SS tables when you write new data. Because of that, you run into two problems, write amplification and read amplification. So they stem from the same problem, immutable data written to disk. In the case of write amplification, what that means is that you can end up with multiple copies of the same data or even outdated data. That data is taking up disk space, and it has the potential for being rewritten multiple times through the compaction process. With read amplification, you have immutable data written to disk. You can have multiple copies of the same data. When you go to read it, that means you might have to read multiple copies and try to figure out from those multiple copies what is the valid value that you actually want to return. So you would think, okay, let's just, we're going to have all this immutable data written to disk. All we have to do is compaction and everything's good, right? Easy. You take all these values that you find over here on the right and compact them down to a single record that has the most recent data, and, Bob's your uncle. Well, yeah, you might want to check the box and say done, but it's not that easy. It turns out that you can't really compact all the SS tables. It's extremely slow, it's resource restrictive, it's using up memory, it's using up disk, and parts of the data may not need to be compacted. So in fact, what you need to do is that you need to operate on a subset of SS tables, and the question becomes, how do I pick what subset to work on? Today we have two strategies. Well, until a few weeks ago, we had two strategies: size tier compaction strategy, or STCS. And in this method, what occurs is that as you get SS tables written to disk, you group them basically by size. So you're looking for SS tables that are approximately the same size. And those SS tables can then be compacted and pushed up a level. So these levels are ways that you can kind of keep SS tables grouped. And this, this one works pretty well. It's a pretty simplistic way to do compaction, but you end up with a few problems. The highest levels end up not getting touched because you don't write really huge SS tables all the way up to the top all that often. Now you have these really large SS tables up there in the higher levels, which are going to take up a massive amount of space to compact them, because this technique needs double the space of what you're compacting in order to do the compaction. And it doesn't really care what it has in the SS tables, so you can have overlapping data in an SS table that doesn't get sorted out when it does the compaction. And there is absolutely no real parallelism that you can do here. So folks came up with another way, which was leveled compaction strategy, and said, well, let's give this one a try. Here, what happens is that a SS table is split into similarly sized tables and promoted to another level. What you end up with is a lot of small tables as you go from level to level. And you can end up with low space. You do have low space overhead to do this because you're splitting them into small pieces, but you may have problems with the triggering the compaction, and there's even more parallelism problems here. So to date, people usually use STCS for my brain just fried. You use STCS for I have a 50-50. Come on, Patrick, tell me, reader rights. Who do I have here who knows about these anyway? Huh? It's right heavy, yeah. Okay, and level compaction strategy is good for read heavy. So you have to take a pick. You got to pick one or the other. I know these things. I just had my brain go crazy. Yeah. Oh, see, I should have gone to my next slide. I told myself, write heavy workloads, STCS, read heavy on LCS. There are some problems with this, though. It's not really easy to tell. Do you have a write heavy or read heavy? What do you have a mixed workload? What are you going to do? Okay, and before UCS, you basically had to pick what you were going to do ahead of time, and you had to set it. And once you had set a compaction strategy, it was hard to change it because you had to do a major or full recompaction, okay, of everything that was there. The other thing was that workloads can change over time. You know, you might have one kind of workload when you start up your cluster, but as time goes on, it may turn into a different workload than you had. So a lot of people have thought long and hard about these topics and done a lot of research into it. And one of the theories or ideas was about using unified compaction strategy. So here we go, unified compaction strategy to the rescue. Well, UCS is all the things, okay? Basically, you can do size tiered, you can do leveled, or you can do anything in between, all right? And it is actually, although it can simulate those older styles, it is actually a new compaction strategy in and of itself, which has improved immensely in a number of different ways. And what is great is that because it can simulate these older styles, you can put it into place in your system, even if you've been running your system for years and years and years. So you can switch between strategies at any time. Literally, you could just change the values that set the compaction strategy, and it'll sometimes kick off a compaction, but when compaction comes around the next time, it'll switch to the new compaction strategy that you would like to be using. The other thing is you can configure the strategy at every level. So you can have a compaction strategy for your L0 level, which is different than your L4 level. And a lot of times that's a real advantage, right? You might want to be doing write heavy at a low level, but read heavy at a higher level. It reduces the space overhead dramatically by how it works. And as we'll talk about, you can parallelize. You know, my computer kept saying that wasn't a word, but it just seems like one, doesn't it? You can parallelize the operation so you can get faster completion of your compaction. And if you've ever watched compactions going on, you know, which are just like, you know, can really make you crazy, especially in a production environment, you'll be happy of that. Lastly, this is a stateless process, so it has that advantage as well. Okay, I'm gonna hope I didn't, I had to pick a level of what to talk about to you guys, and hopefully I picked the right mix of heavy stuff and not heavy stuff. By the way, the guy who wrote this code is in the room, and if you want to know the heavy details, I'm gonna tell you to talk to him. So basically what you can see here is a graph, and in one case, you can see if you're at the bottom axis is a factor we'll call W for the moment, a scaling parameter. And if you go into negative numbers on that scaling parameter, you'll see that your read amplification is really high and drops as you go to the right, whereas the write amplification is low and goes high to the right. The other way around, yeah, okay. The other way around. I should get this right. It turns out that this stuff over here is what you want if you're trying to do writes, and this is what you want if you're trying to do reads. Okay. There's a whole bunch of words here, okay? Levels are determined by the SS table size. We'll talk, it's not quite size, but that's a good first piece. The per level changes will change as you get a higher fan out factor. It turns out that fan out factor can be devised for either that tiered value where you have a T equals some F value, or leveled. If you want this to look like leveled compaction strategy, you could set T equal to 2. And that you will get up to T minus 1, whatever T is set to, SS tables per level at rest. The results will move up a level when they grow large enough. Again, I'm using size. You're going to see in a minute. It's not quite size, and you can make the relationship of F and W as you see here in the two equations for when you have a situation where you have tiered or you have leveled values. So that scaling factor W can be used to basically scale yourself all the way from LCS to a mixed workload to STCS. And it turns out that a lot of times it's much easier to relate W to a value that tells you something about whether you're meaning to do leveled or tiered. Okay, when you set scaling parameters, by the way, in the actual configuration, you could use the integer values. Okay, so for instance, where W equals -8 is the equivalent to legacy LCS, if that's the kind of behavior you're looking for, and it turns out that setting means that your F value will be 10. So L10 is the equivalent of W equals -8. Whereas when W equals 2, you have the equivalent of the size tiered compaction strategy, the legacy, or T4. Neutral is when you're at W equals 0. Because you can set the scaling parameters for the levels, you can see here that you have the option to set different values for each level. And by doing T and L, it keeps you kind of in mind which strategy you're looking at for each level. And basically, the last level that you set will be used for all of the that level and all levels above. So, for instance, I suppose if you wanted to have, STCS throughout, you could just set T4 as the scaling parameter, and you'd have T4 at all of the levels. Yes. Yes. Thanks, Branimir. Yes. The number that's after L and T is the fan out factor. Okay. So I simplified in a couple of slides here that this was size, and in fact that was what was used for the version 1 of UCS, but all of you are super lucky that about 2 or 3 weeks ago, the version 2 got released in Cassandra 5.0. So if you pull down Cassandra 5.0, there's a beta 1 Docker container, Docker image, if you'd like to use that. It's a handy thing to test with. What is actually used now is not size, but density, okay? So what density does is that and the density is computed as the size of the input SS table divided by V, which is the fraction of the total token space represented by that SS table. So why do you care about using density instead of a size or a number? Well, if you think about size and number, I think you can probably, without too much work, realize that you could get some imbalances, okay? You might have a whole bunch of tables come in, and now you're having to do a bunch of work because you have all these tables and you need to get them moved up. Or you have really disparate size SS tables come in, and what are you going to do about that? So the density basically allows you to sort of even that problem out. As the SS tables grow denser, they're likely to move up on the levels, but they also control the size of the SS tables so that you don't get really large SS tables anywhere in the system. That per density level grows by a fan factor, that fan factor again, F, okay, which in this case needs to be greater than or equal to 2. So it also understands the progression of data in the LCS and the STCS cases. So, so even though if you're using basically the equivalent of those older legacy styles, you're still getting some advantage from the density calculations. The overlap in your data in SS tables will allow you to get triggers at the correct points if you happen to be in a mixed state as well. Okay. So what happens with density and overlap? So density, again, it's the size of the table divided by the token share. Now this is kind of an interesting thing. When I was sort of getting into this and looking at the calculations for how do you get density and move on to some of the additional calculations that are behind all of this, at one point I was going over a calculation and I asked Branimir, I was like, I don't understand. How do you get from here to here? And this one you're dividing by a quarter, and in this one you don't divide at all. What's going on? Well, when you're promoting into level 0, you're promoting 100% of that token range. Okay, so my fraction was 1. That was kind of what happened? So. Overlap is looking, you only count the overlapping SS tables towards threshold, and overlap is what usually drives read amplification, right? You have to read from more SS tables if you have a lot of overlap. When compaction is going to actually perform, what happens is that you lump some of these SS tables together in a bucket. And with UCS, what you can do is you can form the buckets from overlap sections, or what's set as transitively extended. So you can see here, here's 3 different examples. You might have 4 SS tables come in, each of which is 100 megabits. And they can be compacted into one large table that has a density of 400 megabits. They could be compacted into 4 tables of 100 megabits still, but a higher density, or in fact, depending on how they get put together and sharded, you could end up with 4 of them that were slightly different sizes, but still have the higher density. So the second part of this magic is sharding, okay? And this is what really leads to the parallelization of the compression. So you can set token ranges. In the initial build of UCS, that was a fixed value. So so the sharding was a set value, and as you'll see, there's been a little bit of a switch to that as we go on. But because you can parallelize, now you can sort of deal with each of these verticals without concurrently, right? You don't have to have them. They're not dependent on another token range in order to be doing the compaction. So the way that the sharding works is that reasonable breakpoints are found. Okay, so you can use reasonable breakpoints rather than just making arbitrary breakpoints that might end up with a lot of overlap because of how you break them up. And this also means that that your compaction doesn't have to have the same rate. It doesn't have to have the same rate across the token ranges, and it doesn't have to have the same rate on the levels. Ooh, let's get some math. So basically, in this most basic idea, really there's only 2 things that determine what's going on for sharding. One is a basic shard count. A lot of times that's set to something like 4, and a target SS table size. If you have the situation, and you're using a condition here that uses the density, the base shard count, and that target SS table size that you're trying to reach, and if that value is less than 1, then you will shard into that basic number of shards. But if it's larger, and you can see there's a little bit of a calculation here. If you want to read about that in more detail, you can go look at the docs that I wrote. But basically what it does is that it means that the number of shards you're set to is a multiple of 2 times the base number of shards that you set. So when compaction starts, the first thing that you need to do is calculate that result density. You use that in the condition to decide how you're going to split the SS tables into close to a target SS table size. And basically what happens is those SS tables kind of get split close to the center. It's kind of like between that value divided by square root of 2, or that value times the square root of 2. And so you can see here in this example that if you set the size to 1 gigabyte, you're really not going to have any change in the number of shards or the size of the files until you get to that 1 gigabyte size. And in this particular case, you'll see that it sort of steps up in shard count, but the size of the files stay the same. that was an interesting way to do it, but it turned out that a little bit better way had a little bit of more of a nuance here. And that had to do with adding a minimum SS table size and a growth factor. So by specifying a minimum SS table size and that growth factor, you could affect the shard count as the data set grew. And so the data on each level could be evened out a little bit. And you can see that now you have one shard at a really small size and three more levels based on the math. The one thing I will point out, is that you'll see now that growth factor comes into the last case, which is where many of the calculations are going to end up with based on the SS table size. And you have a factor of 1 minus lambda, excuse me, in that factor that you're doing for how many shards you're going to have. Who thought they were going to see math today? Okay, so here's that case, all right? We still have the target size set to 1 gigabyte. We've set the minimum size to 100 megabits, sorry. And in this particular case, for the graphs on the right-hand side, you have your lambda value set to 0.33. You'll see that you now have, as the shard count grows, you're actually growing the SS table size commensurately. So if you use a value for lambda of 0, then the SS tables don't grow. If you use a value of 1, the shard count is going to get fixed. And it turns out that if you use a lambda of 0.5, you're going to get the shard count and the SS table size growing at the same rate. Okay, let's go through an example. So here we're going to set a base SS table size of 50 megabits. We have a scaling factors. You'll notice I have it's tiered at the lower levels, and then it switches to leveled compaction. We have a target size of 100, which is twice that base size, and we set the base shard count to 1. Did I? I hope that's right. Okay, so here we go. Compaction, we have four tables. Compaction is triggered. We calculate the shard count. You'll notice that we have a density of 400 megabits with a token range of 1 or 100%, so we're going to get 4 shards. So let's go ahead and write those in. They're each going to have a density of 400 megabits. And we come along, we delete the sources now, okay? We've compacted into new tables. The shard boundaries don't matter now that we're done with compaction. We have a new set of sources come in. So here comes some more SS tables. And this time we have them, they're 60 megabits. That means our density is going to work out to be 240 with a token range of 1 again. So we're going to end up with 2 shards of 120 each. Delete the sources, get rid of the shard boundaries, go on. All right. Now, we've hit a condition which is going to cause us to do a compaction in L1 because we've set that at tier 3, and as you'll see over here, basically if you just think about the ones that are on the right-hand side, you've already gone over that number. So what we're going to do is have to look at the overlap sections that occur between those SS tables. And in this case, you can think of if they're over each other, they have overlap. So it's really easy to see that A and E have overlap, B and E have overlap, C and F, and D, F, and G. But D, F, and G are what actually trigger the threshold here. Okay. So in this particular case, because F is actually involved in C as well, we extend the bucket to include C, D, F, and G. That means that we end up, if you add up all those numbers, you'll have 430 megabits in half the space, okay? So we end up with a density of 860 megabits, and we're going to have 8 shards. If you did those calculations, you'd have 8 shards. So here we go. We end up with 2 SS tables that are 135, and we end up with 2 SS tables that are 80. Okay. Remember that could be within a square root of 2 factor, smaller or larger. All right, and that's in fact what happens here to get those 4 into it. And we delete the sources, and the shards and the buckets no longer matter. And we could continue that, of course, but I think this is where I finish. That example, I just wanted to remind you that the thing that's so important here, for those of you who are operators, you know, and are actually running this stuff, that because the strategy is stateless, you can switch at any time to a different target. The work that was already done will be beneficial even to that, and that the splitting and the sharding is not affected when you make changes. So how do these compare? Well, with STCS, the buckets and levels end up with similarly sized SS tables, but UCS uses a predefined band of sizing. So the selection is more stable and predictable, whereas with STCS, you end up with odd selections of buckets and spanning SS tables of wildly different sizes. They do have similar triggers, but with that additional work that was done, UCS is more efficient about doing it. When there are multiple choices for picking SS buckets within a bucket, picking SS tables within a bucket, STCS will always group by size, but UCS will group by timestamp, which can have some advantages. And UCS efficiently tracks the time order and whole table expiration, which STCS doesn't, which, by the way, there's actually people who have been experimenting with using unified compaction strategy for time windowed compaction strategy as well. For leveled compaction strategy, they end up with a very similar effect, as I said, but in unified compaction strategy, the SS tables are structured such that they can easily be switched to tiered. Tiered US, yeah, to the UCS flavor of tiered, and changed with different parameters. And whereas the LCS SS tables are based on size only, the SS tables in UCS can handle the problem of space amplification by sharding on specific token boundaries. LCS splits SS tables based on a fixed size with boundaries that are usually falling outside SS tables on the next level, which kick off compaction more commonly, and unified compaction strategy aids with much tighter right amplification control. So really, UCS ends up using sort of a combination of both of those techniques, but does it in such a way that it is much more effective for you and uses less resources. That's really the important part. You know, you don't get to say this too often about Cassandra, about an upgrade, all right? I got anybody who's ever upgraded from one to another? But in this particular case, it really is easy. All you need to do is go in and change the factors in the Cassandra YAML, and you got to change, okay? The factors that you are changing are the scaling parameters, target SS table size, minimum SS table size, base shard count. I can't believe I have a typo, and SS table growth. And I can tell you there is way more detail, like I said, if you want to go look at the docs about this topic. So thank you very much. I hope that that gave you some idea about how to use it. Do I get at least a B, Branimir? Yeah. Does anybody have any questions? No? Has anybody tried it? Oh, yeah. Go ahead. Oh, to migrate your actual cluster to 5.0 from, say, 4 or 3 or something? Or? Well, you do have to be using 5.0 to get this compaction strategy. That's where it's introduced.
Typically, when people upgrade, they want to do things one node at a time.
Yeah.
To be sure that everything's working perfectly fine. I don't expect you to have much problem upgrading from LCS to UCS, but for extra safety, I would start with one node and maybe do all the others at the same time, but at least try a little bit
Good answer. When you're testing, always try one node, then do the rest. Has anybody tried UCS? Yeah? And what do you guys think so far?
It was equal to slightly better than LCS in our testing.
Mm-hmm. Okay. The numbers.
I think, I mean, we've chatted about, like, we could auto-range a lot of that. Like, the first one, we could auto-range between 4 and 16, depending on the right wave.
Right.
Right? We could introduce a tiny component of, like, a full compaction across the one node that way. Like, there's some UI.
Right. So, right.
That's, like, super easy to add, right?
So just to reiterate, to summarize, basically, it wasn't difficult to change from LCS to UCS. It was a little bit better. They wish they had some sort of auto ranging to set, and I know that that's been talked about as a future enhancement to this. So. Mm-hmm.
We could do a full compaction within this shard every 10 days to guarantee. I guess maybe this isn't a question. But are there any ideas around, like, making tombstones find their data? So, like, that's what
Oh, yeah.
within a shard, there's like a time-bounded amount of time.
Yeah.
So we don't have
Answers for tombstones. Yeah. Yeah.
your ideas are something that we
Mm-hmm. Yeah.
It's moving us in the right direction.
Yeah.
We've used
Good.
some UX improvements, but we're on the right path.
Good. Okay. Well, thank you all for coming today. Mm-hmm.
Mic me up.
Yeah.
Testing. Okay. Is that okay?
Yep.
Hey, everybody. Can you guys hear me okay? All right. Okay, hey, everybody. We're going to get started with the next talk. We can continue having conversations outside if you'd like. My name is Rahul Singh, and I'm so excited to be here. Cassandra Summit has not been Cassandra Summit for years now, and I'm really happy to be here. I'm also super excited that we're talking about AI. And when they asked me to potentially tune this talk, because we decided to do these summits together, I said, you know what, there's going to be enough talks about AI. So I will cover a little bit of AI today. But my goal is to come across with 3 points. One is, how do you design an open data platform that can withstand personnel changes, people coming and going, technology changes as technology comes and goes, right? Number 2 is, how do you do that in a way that future-proofs you for more and more AGI or AI coming down the pipeline? And number 3 is, how do you control this? How do you keep control of it? We're at an open source convention, open source summit here. So it's not necessarily about everything happening to be running on your hardware, but it's really, do you have control over the software, okay? So the biggest challenge, I think humanity faces is that people are going to figure out, they got to figure out how to steer out the computer while robots do the work, right? I think if you don't know that, trust me, even as smart as you guys are, how do you steer at your computer while robots do the work? You're going to do it, because you're going to be running an LLM-based application, and you're going to be watching how it runs, right? Half of this is a joke, but half of this is true. And this will come full circle when I talk about, how do you build a data platform that is AI ready, right? That AI can help with later on. But really, it's about the knowledge management. You can design a good data platform. You can have the right engineers. You can have the right technologists. But how do you manage this process of designing and building so that new people can come and help you design and build? And at the same time, you as an organization become an expert on that platform. There's no 2 platforms that are built the same. Every single platform is different. And we'll work with DataStax a lot. And DataStax being a product company, they're always like, this is our product and it can solve these problems. I'm like, yeah, but this is the industry and this is their problem. How do we solve it? How do we work back from that? So I'm going to cover a playbook for how to design a platform, an opinionated framework for reference architecture, and the approach for knowledge management. And we're not going to get to the migration use case, but we're going to look at a standard data fabric, and we're going to talk about cloud versus open source or open core. These badges you can collect later, but there's 3 badges I'm going to give you. The deck itself, you can get this deck. There are going to be high-resolution images of the things that I'm showing that I think will be useful for you to take a look at later. And then a link to a boot camp that I'll be doing around generative AI, specifically with modern data platforms in the mix. So our company, shameless promotion, we help platform owners go beyond their potential. That's why we work with Cassandra, because Cassandra is infinite. And we do this using our playbook, and that's what I'm going to be talking about. And our playbook is basically a set of principles. Okay? We worked with a lot of logos that you probably interact with, and these logos, they end up using databases like Cassandra because that's the only database in town at that point that'll work. All right? At the end of the day, you know, we look at our company as a people and knowledge company. Ultimately, we're solving problems for people. We're solving challenges. Modern technology is very disconnected, right? This is a picture from 2020 of the marketing technology stack. And in a consumer-oriented company, the marketing stack is where a majority of data comes from. And how do you consume and how do you process that information so that it can help you make decisions, right? And then you have on the bottom right side, this is a tech stack of all of the open source LLM frameworks and tools and AI tools that are out there. So technology just keeps getting more and more complex. Not because the technology itself is becoming complex, there's another player, there's another player, there's another player. But what do most people need? Most people, they just need a way to find information, right? Analyze it and act on it. It's usually these 3 things, right? And I joke that, you know, database technology is been the same. Get your stuff into the database, get your stuff out of the database. But as people use it, it's about retrieval. It's about finding. Visualization, one way to do it. Analyzing the data could be one way to do it. And acting and sharing on it could be another way to do it. And just put in the back of your mind, ask yourself, where does the AI fit into this? Because the AI can help with that stuff. Business platforms, mature business platforms, they actually cater to 4 different kind of audiences: employees, partners, customers, and let's just say things. And I would maybe add AI later on as services that are going out to people. It's a customer experience. If it's a information system like a CRM, if it's a business intelligence dashboard, right? I didn't make this diagram. This is from Gartner's, you know, business technology digital platform or something like that. And big companies have hundreds of systems that they have to organize in order to have a business platform. And for me, the nirvana is all of your stuff together, all in one place, so you can find it, use it, share it, and going beyond the 12-factor app manifesto, which is the data available for the people at the right time? Is it available in real time when it needs to be? Is it available behind a password because it's sensitive information? Is it up all the time? Is there a recovery point objective and a recovery time objective of 0? Because that's what's possible with technologies like Cassandra. So this is what I'm thinking about, is if in a perfect universe, all the data being generated in an organization could be in one place, the ability for the company to use that data allows them to, with human hands, with AI hands, basically make decisions quicker, better, faster, to be cheaper and better than a competition. All companies go through this sequence, by the way. You bring up silos, you create standards, then you create standardized data, and then eventually you can have standardized processes so that the company can do new things quickly. And the value of the organization's technology depends directly on how your optimized data core is being built and managed. Because if a company acquires another company, how quickly can they integrate that company's resources? It's not about the technology. Eventually, it's really all about the data. Today, companies are using things that are outside the firewall, right? They're using apps, software as a service, QuickBooks, Salesforce, et cetera. The standardization is about containers. It's not about, Windows versus Mac versus Linux. It's about, are we using Kubernetes or are we using Kubernetes? And the optimized data store is, I think, a little bit harder to handle because not every database can handle every problem that you have. And if you're a big company, you can't just get, one database, right? If you're a big company, you can pay millions of dollars and get Oracle. But if you're a company that wants to scale in a growth perspective to be able to cater to millions and billions of users, you can't go down that route. That's not going to work either, right? The goal is business-to-business modularity. How can you make your platform in a way that allows you to connect with those other people I just talked about, customers, employees, partners, right? And eventually things and maybe AI, in a way that if the shifts in business change the direction of your company, you're able to pivot much quicker than if you didn't have this stuff together. Generic data platform, you guys have all seen it. Data in, data out. Every data platform has some component of this, scheduler, streams, batch, right? Data comes in from different sources, it goes out to different systems. What Cassandra does is, because of cross data center replication, it allows us to have the same data set being acted upon with completely different tools. So in this case, we're looking at one that is running Spark, machine learning workload. We're looking at one using Presto for reporting, and another one, and by the way, Presto can run on, or Trino can run on Spark, so it's not like they're mutually exclusive. And then another one that's doing all the transactions, apps that are built on Node, on Spring, on Akka, right? This allows us to have this data fabric, and because it's open source, you can choose to have this in AWS, in multiple regions in AWS, in different clouds, or half of it on your infrastructure and half of it on the public cloud. So these data centers can really sit anywhere. Talking about design. When we think about building a modern data platform, you would say, okay, what are you using for infrastructure automation? What are you using for orchestration? Actually, I say, let's step back for a second. Let's think about who's going to be using this. What are the processes that they need to be responsible for? And that's really where the design component is less to do with the technology and really to do with the business goals. There are tons of modern stacks out there, right? If you look for a modern data stack or modern data platform, you'll find a bunch of things. They usually have Snowflake, dbt, Databricks, right? Spark. So which one do you decide to use? How can you decide with this, and then it just continues to grow. And every day you go, there's another logo that you have to take a look at. Our approach is to look at people, processes, information, and systems as an inventory, and then ask, how are we taking this most important business process and making it better? The framework, it's comprehensive. It's about the user experience platform. What are we using? What data system are we using? What cloud are we using? And the approach is less programming, less scripting, and more configuration and automation. I can't obviously go through every single step here, but your company will have some version of this. The point is, can you take your approach to your platform and teach it to that person that's coming onto your team tomorrow? And then can you take that same approach and teach it to the LLM that's going to be assisting, right? Because if you're going to be scaling an organization, yes, you can always add more technology. You can always add more compute nodes. But when you need to make more features, it's going to be people, at least for now. So we use a canvas. You guys have seen a business model canvas. You guys have seen Lean Startup canvas. We use a canvas that basically takes two dimensions: people, process, information, and systems. These are our contexts, and then responsibility areas. So you can basically inventory every single person or persona. What are the major business processes? What are the major information requirements for those processes? What are the technologies that it's running on right now? To find out potentially, are there redundant systems? Are there processes that could be sequenced together? You can zoom in. For example, this is a design for a data platform where there were customers, business owners, engineering, and operations. Every business that's of scale has, obviously, customers, the business product owners, right? What are their goals? Well, in one case, it's to add data reports and integrate data, right? The business product owners, they want to release and support customers. Developers and engineering, they want to develop, test, release. And operations wants to support infrastructure. If you think about the goals of each of these users, they're not trying to fight each other, but sometimes it feels like that. But when you put it all in one place, you can show them that actually they're trying to do the same thing, right? They're trying to help the customer out. And what we found out here is that there's actually very little overlap in terms of the data requirements between customers and business product owners versus the engineering and operations. And people were expecting there to be more overlap. In our framework, we go through a simple checklist. Is it distributed? Is it real-time? Is it extendable or open? Is it automated? And can it be monitored or managed? You can do an architecture on Amazon, public cloud, right? You can do an architecture on Microsoft Azure, public cloud, sure. You can do an architecture on Google, public cloud. Are they all distributed? Yes. Are they all real-time? Yes. Are they extendable? Yes, they all have open, usually they're all open in terms of APIs, not open source, right? Can they be automated? Yes. Can they be managed or monitored? Yes, absolutely. So being a distributed platform does not mean that you have to use open source. But the case I'm trying to make is you should look at open source as a priority because you get more freedoms when you're using open source. If you look at the ecosystem, there are tons of specialized databases that are out there. There's tons of streams that are out there. There's tons of stream processors out there. So how do you use this stuff, right? There's lots of data modernization, automation, integration tools out there. Who has done ETL with the no-code, low-code tools that are out there? Anyone? Like Airbyte or Grouparoo? Okay, I didn't think so. It's relatively new. In the whole ecosystem of business software, no-code, low-code, I believe that's the future, right? And all of these tools basically help facilitate automation and building of systems without too much programming. And when you bring it all together, I look at it as a computer. There's the major components of a computer, right? You have your RAM, CPU, disk, display, motherboard, operating system. And the way I correlate that is persistent queues for RAM or bus, right? Queue processing for and compute for the CPU. Persistent storage, a reporting engine for the display, orchestration framework for the motherboard, although you could argue that the data pipeline could also be that, and a scheduler, which is the operating system. And then there are strategies. There's cloud native on Google, for example. Self-managed open source, self-managed commercial source, managed commercial source, right? You don't have to take one approach to the other. You can say, you know what, we're primarily an AWS shop, and there's nothing that's going to be better than S3 for what we need to do. We're not going to bring up a MinIO cluster for S3, right? And you can decide to use managed Kafka services for Apache Kafka from, I forget, they change their name all the time. But you know what? We're going to use Cassandra for our database. And we're going to use EMR for our Spark. If you have this grid of the different strategies with the different parts of a data platform, it allows you to make choices based on your business. There's a reason why somebody is going to be happy using Elastic MapReduce for Spark versus Databricks, right? There's a reason why somebody would be happy using Google Dataproc for Spark versus, self-managing their own Spark cluster, right? These decisions aren't objective. They're all going to come down to a business and their goals. What this approach asks you to do is to do the homework. Look at the ecosystem. Look at the grid of what are the things that are really important in a particular business. this diagram is going to be available on the downloads, so we're not going to go into it. But in this, what I've done is collected basically all the open components for a distributed data platform and added to it things like no-code, low-code for ETL, reverse ETL, as well as low-code, no-code for user interface. And the goal with this is that when we are thinking about a scalable data platform, that we have a starting point. We don't necessarily have all of the choices made for us, but we have a starting point. And in here, there's Astra and Cassandra and self-managed DSC as an option, because all three of those can do something very specifically. At the same time, for the query layer, we may end up using Snowflake in some instance, and we may use Presto in another instance. And then finally, the approach. The approach that we take to managing platforms is making sure that we have at least one page for every component and every platform that has the following schema of knowledge documented. How do you set it up? How do you train on it if you don't know what you're doing? How can you do basic administration? What does the configuration look like? Where is it stored? And what are our external links to knowledge? It could be Jira tickets. It could be a blog for an expert. It could be a YouTube channel, right? And periodically, a person that owns the component will go and update that. I know that this is a technical conference, but trust me on this. Knowledge management is a big differentiator between teams that perform and teams that don't, right? And I didn't even come up with that. Like, that's a McKinsey study. 75% more efficiency if you have good knowledge management. But think about the AI that's coming. Think about prompt engineering. The more relevant data that you can give that AI to build things or maintain things for you, the better it is, right? So it's not just like you're preparing for today. When you start documenting systems in a structured way, you're actually preparing for the future. The full schema is available on the download, but it can go deeper. So if you want to go mature the knowledge base beyond one page per component, you could technically go and have a whole page per section, or a whole wiki site just for a stack for one component or one platform. I separated it out basically into two sections. Every framework has a platform, and there are components that make up the platform, and then there's extra resources. And so what you'll see here is that the components of a platform could be the infrastructure, the compute, the data, the cloud components, open source components versus cloud native components. This may seem heavy, but if you do the work and you have a README in your repos for every system out there, you kind of already achieved this, right? It's really about having a structure in place that you can tell people where the things are. We talked about data fabric very basically, but I'm going to go a little bit deeper, and I'm going to wrap up. Getting data into Cassandra is hard. It's getting easier because there are lots of no-code, low-code tools that are out there. Once you have data in Cassandra, you can serve it up more easily today with things like Stargate. Right? It creates an API on top of your tables with GraphQL, JSON REST, gRPC, also a document DB. And the idea of reverse ETL, which is a relatively new concept, you can do that today as well, where you take data out of Cassandra, low code, no code, and synchronize it back to your systems, right? And when you put it all together, what you have is kind of this unified data fabric that can bring all your data together for a business, process it together, and send it back to where it needs to be. In an ideal world, your users don't even have to use a new system, because you could just be materializing information into the apps that they're already using. And then you can add to that LLM engineering, right? Before LLM RAG engineering, ML was very hard, right? Now, machine learning ops is optional, but what is it about this new kind of pattern? What is it? It's really another workload. It's a workload for getting data in, processing it with embeddings, and storing the data. So if you think about the larger ecosystem of what's possible with Cassandra, it's not just, REST APIs. You could be storing features for ML models and serving them up in real time. You could be training features and models in real time. That's what Cassandra gives you. It's the ability to do all of this at once, in the moment, in real time, and not break at the seams. If you try to do this with any monolithic database, it's just not going to work. And this is where, at least in the vector database world, the monolithic vector databases are not scaling because they're just not built like this, right? And because Cassandra's been around for a while, there's lots of tooling out there. There's an ecosystem of tools. When people say, why Cassandra? I'm like, okay, when there's Keyspaces at Amazon, Cosmos DB, Yugabyte, and ScyllaDB all copying Cassandra, obviously Cassandra's doing something right, right? Obviously Cassandra's doing something right. Why is it that CQL became the protocol for structured not only SQL? Who knows? But it is what it is. Takeaways, I would say, don't reinvent the wheel. Just identify the objectives. I think a lot of times in the data platform world, it's like, oh, we need to warehouse all the data. That's not the goal, actually. The goal is somebody using it. It's somebody using it for some job that they have, some goal that they have. Prioritizing DevOps and data ops. Automation is the key for a modern data platform. People should not have to stare at their screens while a batch job is running, right? They should not be looking at the log analytics, sitting in front of their computer to make sure a batch job is running okay, right? Or a real-time ETL app is working okay. Use open tools. Obviously, it's about open platform, and then basically to document the stack. If you document the stack, you're going to be fine. Thank you. Dream big. The whole deck is available with that QR code, and I can take any questions if you have. I knew this was going to happen. So I do a boot camp on large-scale LLM RAG engineering. You're welcome to go check that out. We did one earlier this year with a partnership with DataStax. With so much that has changed, we're going to have to update it. But the goal is to get people from zero to hero, looking at the whole RAG LLM engineering skill set and getting them up to speed to be able to build a large-scale LLM application. Quick preview of the agenda. It's strategy and theory, which is important if you're going to be looking at this long-term as a career. Design patterns that are out there. There are no-code and code LLM stacks, if you will believe it. And building a custom chatbot with LLM for your own data. And if you don't believe me, come to me later. But I built a production scale LLM app using Astra and Bubble in an afternoon. So I know I can do it, and I know you guys can do it too. And with that, I'm going to wrap up. So thank you so much for coming. Appreciate it.
I went crazy with the slide deck, so even with talking fast, I think the time will be kind of tight. So at 4:21, we'll start.
And then you want to turn your mic on.
Oh, yeah.
It's nope, it's down in your pocket.
Thank you. Okay, is that better? Okay. I public speak so much. Okay. Okay, guys, I think we're going to go ahead and get started here. My name is Colleen Velo. I'm standing alongside Jeff Beck, and we're going to be talking about smart things with Cassandra for the first 9 years. It was 8 years when this talk was originally envisioned, but due to the rescheduling, it got changed up to 9. So, like I said, my name is Colleen Velo. I started working with Cassandra when I joined SmartThings in 2015. So, I've been with SmartThings about 8 years. I'll toss it over to Jeff.
I'm Jeff Beck. I've been doing Cassandra for about a decade. I'm aging myself by putting my MVP award up there, but I'm still really, really proud of it.
I'm really proud of it too. So, okay, so for the agenda, what we want to do is kind of set the landscape of where we started with Cassandra, talk about how we've progressed through the various challenges, including problems of scale as you usually get, and then kind of settle on where we are present day and kind of the lessons that we learned through our journey. So, SmartThings at a high level, in case people aren't familiar with it, is basically an IoT platform. We were acquired by Samsung in 2014. And God, how many? I think we have over like 200K events processing through our system now.
You forgot to say a time period. 200,000 events a second.
Oh, thank you. Yeah, 2,000 events per second. Thank you for the correction.
Just 200,000 events total.
Yeah, no, per second. So at a high level, kind of walking through the timeline paradigm here, like I said, Samsung acquired SmartThings in 2014. 2015 was, you had a single application, monolith, single Cassandra ring in a single region, in a single repo. So the way most startups start. 2016, started expanding out into different AWS regions, which meant the rings also expanded out into the different AWS regions. We also set up our first global ring. And so we had several shard level, well, I'm going to say region level rings, and then a global ring with multiple data centers. So moving on to the middle time, that's when we started the One App launch. And basically, that was kind of the merging of SmartThings had their own mobile app. Samsung kind of had their own mobile app, and we wanted to merge it into one brand. So we did that, as well as starting to onboard Samsung TVs as OCF devices, as devices. Yeah, forget about the OCF part. After that, then, there we go. After that, in kind of the mid data center or the mid journey, started doing redata centering, and that's so we could both expand out, and we started doing some stuff with more embedding of hubs. And then fast forward to today, more Samsung appliances, which are coming through as devices, and full microservice model with the monolith decommissioned. So, starting at the beginning, like I said, it was a single monolith app, single DC, single US, monorepo. We expanded out into the 2 regions. We was using the EC multi-region snitch for that because at that point in time, AWS did not have multi-region peering. That didn't come till 2017. So we were on public-facing networks. Some issues or some challenges that we had: backups, restores, repairs. We was on DSE DataStax at that DataStax Enterprise, which is what DSE stands for at that time, and Ops Center. The solution for backups and for the repairs that was being offered by DataStax didn't quite work for us at that time. We were on an older version of Cassandra, and that probably played into it. So we ended up with a home-rolled solution, which also had some shortcomings. It locking issues, there was a lack of monitoring, there was not a lot of visibility into the job status, et cetera. For the monitoring metrics, we were using the DataStax Ops Center, which, I did like the color coordinated, if your cluster's running hot or if it's in the yellow or if it's in the green, but you were limited on the metrics that you could get from that. It also, as I recall, didn't have a strong RBAC model, so only we could look at it.
Yeah.
Yeah.
The RBAC model was okay, but we also didn't have a super mature authorization inside the company either, so we kind of solved for that by limiting people that could touch it, because that's easy.
Yeah, so the long story short, only the sysadmin people could look at it. The devs often could not look at it. So configuration management, we were using, again, kind of a home-rolled script for deployments, written in Python. So
the application side, as we look through this, we were at a place where we were trying to scale Cassandra to lots of the company all at once. And so we took the effort to say, we're going to build libraries that have opinionated, best practice settings baked into the libraries. We switched over to doing a lot more in the open source world and saying, look, in the framework, let's build the connections deep into the framework, things like Cassandra, Ratpack and Drop Wizard, and tying that into the execution models, native promise frameworks. That was all really important to our developers. And what we were working on here is really saying, let's, in the early years, abstract away as much as the details of the inner workings of Cassandra from it. Now, the timed and windowed compaction jar is something we actually started. Time windowed compaction jar is something where this partnership between our operations and application side became really interesting. So we were facing the need to start building and deploying a jar with all of our instances because we wanted to use time window compaction before it hit mainline. Absolutely amazing thing, but if you have a traditional relationship with operations, that's challenging. And so app teams were like, oh, we write everything in Java. We can build a pipeline, our own pipeline, to make sure we have builds quick, and did all that. So that was the kind of partnership that was really exciting in this era. So we would build jars. You would somehow make it appear on every server for me, so I didn't have to worry about it. Yep. And then we continue to move on.
So that was the beginning years. Kind of the mid-years, what was happening with the architecture is we still had the monolithic model, but people were quickly realizing that that was not very sustainable nor scalable, especially at the rate that Samsung wanted to expand. So we started microservices rollout. If there was any new functionality that was needed, it was developed as a microservice and not bolted on to the monolith. And we started the very beginnings of starting to chop off functionality or migrate functionality out of the monolith and into microservices as well. So the start of that activity was happening here, as well as the one app launch, which again meant more rings.
Scale.
And much more scale. We also started expanding out into the China region, again, more applications and more Cassandra rings. And we started to encounter very significant problems of scale, highlighted by the Super Bowl, where we had kind of a bug in one of the TV apps with the volume up and down, which Jeff will talk about a little bit more, but basically it would just cascade our platform with events. So for operations on the Cassandra side, we did another iteration of the backup tooling. Went away from the cron job because it was somewhat unreliable, and we had problems like I had mentioned before with the locking and visibility. And we had somebody kind of do another in-house solution, Groovy-based, and they wrote another backup solution for us, which did work well. We had a process in place where we tested it daily, mainly using it to populate our analytics Cassandra clusters, which were fed into business Datadog graphs. We also changed our monitoring and metrics. At this point in time, we shifted away from using DataStax Enterprise, and we went to just open source Apache Cassandra, mainly derived from financial reasons. We wasn't using really the DataStax Enterprise features, and the Apache Cassandra one satisfied our needs and was very cheap in that being free. So with the backups and restore, the solution was a lot better. It was a lot more robust. It was reliable, but we still had some sharp edges around that. Single point of failure. The person who wrote it was the only person who really knew it in depth. Ironically enough, it also ended up being a monolithic code base because it did more than just the backups and restores. It was kind of the developer's personal tool bag, so we used it for a number of Cassandra-related activities. And there still was a lack of monitoring and visibility, you know, if it failed if it ran correctly or if it failed, et cetera.
To give a sense of scale at this point, it's one global ring across 3 regions, and then regional rings at the order of 6 or 7, and of course China being special because China's isolated tool stack, just to give the picture of what we're talking about.
Right. When we moved from DataStax Enterprise to Apache Cassandra, we had to change up our monitoring. We lost the nice GUI graph, and since the rest of the corporation or the rest of the enterprise was using Datadog, we kind of doubled down on our Datadog graphs. We already had a couple of them, but they were fairly thin, and so the nice thing with that is, one, we ended up with a lot more robust graphs, monitoring a lot more metrics in a lot more detail. So following along with that, we could put in a lot better monitoring, a lot more early warning systems, you know, to obviously know about any issues or trends before the developers do. The other nice thing about that, it was kind of gave us a single pane of glass, so the developers could actually take graphs off of ours and embed it in their graphs on Datadog. So it was just, there was a lot more exchange of information for the developers as well. At this point in time, we also started splitting, not Cassandra yet, but some of the other apps off into their own repos. One of the things of expanding into the China region is it kind of highlighted the limitations of trying to use a monorepo for all apps, all infrastructures, et cetera. Of course, like Jeff had alluded to, or Jeff has stated already, that meant more Cassandra clusters as well. And at this point, we stopped using the EC2 multi-region snitch as the default snitch for global rings and started using the gossip, sorry, I always mess that up, but the gossiping property file snitch as the default one.
No one can say it correctly, it's fine.
Okay. GPFS, thank you, yeah. So the advantage there, which I'll cover in later slides as well, is with the EC2 multi-region snitch, it is pretty much hardwired to take the DC name, the rack name, and it also requires you being on a public interface. That's actually hardwired into the Java class. And like I said, cross-region peering wasn't available at that time. At this point, it was available, and we wanted to start bringing our rings inside and having them run on private networks. One other thing that we did at this time is we migrated from direct attached storage to EBS volumes. There was a lot of discussion around this, and probably a lot more discussion could be had, but the main reasons why we wanted to do that after a lot of performance testing to make sure we wouldn't take any performance hits was we was hitting the issue where some of our data was growing so fast we needed the ability to be able to get more disk space very, very quickly without having to constantly roll clusters. The other thing is that AWS was kind of starting at this time to offer more newer instance types with EBS backing versus direct storage attached volumes, direct storage attached. And that trend seems to be continuing, unfortunately. The nice thing here is that with EBS backed, it gives us the ability to be able to roll the cluster or do AMI rolls very, very quickly. All of our clusters are on AWS, and I probably should have said that at the beginning, so we're entirely in the cloud, nothing's on-prem. So if we have a zero-day exploit or need some security fixes, we can quickly tip up a new AMI and just bring the EBS data volume back and keep moving without having to keep restreaming all of the data. The one thing that you do have to watch if you do use EBS is you really need to watch your IOPS and your throughput and make sure that those are really tuned so you don't risk having throttling on your Cassandra cluster. And I'll throw that over to you.
In the application, this is where we've had lots of fun stuff going on at this era. Looking at those move to Datadog was incredibly helpful because me as the application developer side, I started to pull more and more of those graphs deeper into my production monitoring, understanding, this is a write or a read heavy thing, and I see how the cluster is contained. Where we tended to like divvy it up, like compaction settings, stuff like that, tended to be application concerns in our world, not as much operations. Operations had to make sure all the compactions were working, and they would come and be very nice about me waking them up when they weren't working because I messed them up or something like that. But that's where that partnership was really evolving. And then at this point, we had to start hard coding the driver versions. So I don't know if anyone remembers, there was a bug for a while on protocol version upgrade where if one of the nodes during a release was upgraded, it would upgrade all future connections. It's a bug, it's well documented. We just then went to the stance of saying, okay, well, we're gonna set the protocol version in the settings on our application side. And that's the thing we had to know to make sure, again, we can do zero downtime deploys. This is also where, I believe this is the era where we ran into the interesting bugs of if you're using select star in prepared statements and then edit your table, the order of the select star fields are gonna be out of order. Simple stuff, but again, this is in the application world, we weren't as deep into that. If anyone doesn't know exactly what I'm talking about, just don't use select star in production, just write out your fields and it'll be fine and you can forget it. And that's the level of like, we were trying to make those best practices. And I don't know how much code is out there that all had select star that I 100% wrote myself. Like, that was from those early years when we had that one thing. We weren't making that many changes, but then as we expand, that's exactly what's happening. And that's where we see, again, these earlier decisions start to come back and mess us up. But they work great to scale early. And right now, this era is working fine.
So then we come to the era, I'm going to call it the redata centering era, because basically we went through and completely rolled all of our clusters. And going back to what Jeff had just stated, when we initially set out and set up our Cassandra clusters, for the most part, we used a lot of the default values. Not in all cases, but for most cases. And in some cases, speaking specifically here, num tokens, the defaults really were not particularly good. Thank you. So with that, we wanted to change the num tokens to be able to do, if you have your num tokens too high, any streaming, as people who work with Cassandra will know, any streaming operations that you're going to do is going to become that much more painful, whether it's repairs or whether it's, bringing in new nodes, expanding, shrinking, what have you. Some other challenges that got thrown our way is AWS decided it was going to decommission one of its availability zones, and when you're running Cassandra in the cloud, basically an availability zone is pretty much analogous to a rack. So basically they were going to decommission one of our racks, and so we wanted to basically bring up a new rack in the new AZ without taking any performance hits or obviously any downtime. Kind of alluded already to changing cluster level parameters. We wanted to change the endpoint snitch as well for our running clusters. And in some cases, for some of our rings that had a lot of high density nodes, although not as high as some, we wanted to be able to resize those up fairly quickly without having to spend days and days of restreaming data for that. So I have a note for the last Pickle article there. We followed a lot of the stuff in that, and we also, unfortunately, suffered a loss of a data center as well. So being able to bring up a new data center, configure it the way you want, rebuild all of the data in it offline without any applications going to it, and then saying, okay, we're ready, and being able to push it over to it bought us a lot of value. At this time, we also made another adjustment in our repair tooling. Before, we kind of had an in-house solution, which was very, very poor, and resulted in us not doing repairs nowhere near as regularly as we should. So we went with the open source Reaper tool, which was developed by Spotify, and rolled that out, and that has been working pretty well.
So for us in the application side, thinking a little bit about all of the current data centers and all of that like best practice that I baked into the tool in the early years, yeah, it was mostly wrong at this point, given our scale and what we were doing. So we had to go back through and change a lot of our drivers. That's when it started, our wrappers to those libraries. Now, it made sense when we were smaller, moving fast, and we deployed a lot of these things weekly or faster in many cases. But these had become really solid systems. Our auth system at the time is completely backed by Cassandra, and it runs through everything that you can think of for IoT because auth is incredibly important. I can sidebar about that with anyone that wants to talk about auth. It's a fun hobby. It weirdly is for me. And then we also started to need to point apps not at the data center they're turning on in. So we had the configuration and these libraries set up so that when you turn on an app, it's like, oh, I know I'm in EU. I'm going to connect to EU as my default data center in the driver so that when you have a multi-region deployment, it knows to send most of your requests there. And it's also, again, we want to reduce our spend on network transfer, so we're trying to align to the availability zones within the region and all of that. So we're trying to align all of that. And this is where it turns out we over-indexed on making it easy, and we needed that control and flexibility because we lost a data center and we're doing migrations where we have two clusters in the same region deployed, and we want to be able to be more specific about what we're pointing to and moving around. So that's mostly there. And then I think the rest of this era was really, maybe read the dates if you understand why it took us a really long time to do this safely, because we were also, I think, learning how to do it very distributed, opposed to getting together in a room and doing it all at once. We got really good at doing massive data center migrations with little to no impact across running production, where we were also getting an incredibly new set of like operational concerns, because at this era we're also seeing massive shifts in how people use their smart home, because so many people had shifted to working at home during this era. So like we're operationally seeing massive shifts that were like, is this anomaly? Is this the new normal? I don't know, I need a nap is usually my answer for that one.
Yeah, so fast forwarding to present day, the Monolith app has been sunset. We're up fully on a microservice model. We have over 300 plus microservices. Cassandra, I forgot to mention in the redata centering years, Cassandra also has been moved, each of the rings have been moved off into their own separate repos. So your blast radius is a lot smaller. If you're making changes, you only risk making changes to that one ring. At this time, we're also using Spinnaker for rolling out deploys, and so you now have the concept of a canary where you can, in our case, we call it a jailed node, where you can bring it up, take a look at it, make sure that stuff is set the way that you expect it to be set, et cetera. And we're also seeing Samsung have, Samsung devices, a lot more Samsung devices coming through to our platform, which basically equivalences to more events coming through for us. At this time, we also retooled our backups and restores, and we're now using the open source Medusa, which has solved a lot of the shortcomings that we've had before. So now we do have good monitoring around it. We do have good visibility into, if it's running properly or not, and all of the other pluses that you get with using an open source product. No more single point of failure as well. Like I said, for configuration management, we're using separate repos for each of our Cassandra clusters. And we're using Spinnaker for the open tooling and deployment. I don't know if you want to say.
The application we finally got to deprecate. The Monolith was great. The reason that is particularly interesting is it had very old versions of drivers, things like that. So getting rid of those. Generally, the Java drivers have done really good against different versions of Cassandra. It's generally safe. It makes me really nervous just because that's the type of person I am. The other thing, application side, that is kind of coming out with this is, it's not really something to call out so much as we pulled out all of the like baked-in configuration that we had baked in as best practice. That's all gone now. We're more collaborative, but we have a much deeper trust for backups and restores for that, and that allows us the things like testing and automatically backing up, like using our automated backup to restore to what we consider analytics clusters.
Right, which we were doing with Medusa as well. I forgot to add that in as well. Go ahead.
App-wise, that's really good because then as my application developer, I don't have to let anyone touch my running Cassandra cluster except for me, because I don't share.
Yeah.
Well,
So,
I don't.
So kind of at, kind of the high-level lessons, we did do a couple of, roll your own solutions, and there definitely is a time and place for, having to do a roll your own solution, but generally speaking, in our case, for the most part, on the operations side, we've gotten better results out of the open source solutions. That being said, the open source solutions had matured since the time that we did our roll your owns. So another big takeaway is not trying to double down so much on multi-tenant clusters. That proved to be troublesome as far as troubleshooting, as far as tuning. We did have, at this point, we have 2 global rings and any number of single DC rings. And in one of the rings, we had a write-heavy and a read-heavy workload, and so it was just a nightmare to try to tune that. We've had cases where we've had the noisy neighbor where one app was not misbehaving, but definitely sucking up a lot of the resources to the point where it was affecting the other ones, et cetera. So right now we try to keep, single app per cluster, which keeps it a lot simpler. And another takeaway is really minimize the time of running mixed versions clusters. That one I will really stress. When you're trying to do an upgrade, really sit down and plan that window pretty carefully. Basically, your cluster is, most people who've done upgrades know your cluster is pretty much locked at that time. You cannot do any topology changes, you cannot do any schema changes, or any streaming operations. So yeah, really try to minimize the time that you're running mixed versions.
It sounds simple, but like,
it does sound
we've
like
both been
sounds
burned
like a
over and over. So yes.
I would put that one in red if I could. And I'll let you do the.
So for us, the takeaways, depending on where you are in your application journey, right now, I would say, minimize hard-coded values. If you have good config management, figure out how to instill the best practice. But if you can't, it will last you a few years. You can get by 3 or 4 years if you hard-code all your best practices into a library and distribute it in your. But just remember that you left it there. Don't forget, like I did. We had a number of weird anomalies. That's oh. Right, that one bug where we pinned to version meant that we never went back through and cleaned it up 3 years later, and then we had to go through and clean it up. It's those simple things, but those are application level concerns that you need that deep partnership. And again, the whole minimizing hard-coded values, that's true, but remember you're gonna add that cognitive overhead for your developers that are all about it. And just, again, always partner deeply with ops. We're up here together because the best outcomes that I've ever seen in Cassandra is when the application teams and the operation teams are working together. As soon as we got those metrics on the same dashboard as my application, it's been amazing. I remember looking at IOPS bursting issues with AWS at the same time as my upper level throughput. So that's really fun, and it's also where when you make a mistake in your app code because nothing has changed in all of here, and then everything suddenly turns red, and you're oh, I definitely did that to them. Sorry. Yeah,
no problem. Apology accepted. These are some resources which has been helpful for me when I've gotten into various files, various fires rather. The AF Slack channel I found has been very responsive. I've gotten a plethora of information from the last Pickle blog. I highly recommend reading that. John Haddad's blog also has a lot of very good info, especially around tuning. And the data stack Exchange, also very good. Same thing with Planet Cassandra. And then there's the Apache Cassandra Corner podcast, which there's an episode where Jeff has been on, and which Aaron Plotz here does. So recommend those resources. There's a lot more, but these are kind of my top picks. So thank you very much for your attention. I appreciate it. Any questions?
And someone could check us on time.
No, yeah, we're right on the time.
We'll answer questions until the nice man that runs all the AV kicks us off.
Yeah.
How much of a heads up did you get on having to decommission those AWS areas, and how long did you have it planned versus how long did it take to do that migration?
We got more than enough heads up
Yeah.
on paper, but never enough time in practice.
That's an accurate statement.
Yeah, always.
Yeah,
Um,
yeah. So
Go ahead.
Yeah, I was going to say, once we had, there was a couple of it affected thankfully only a small subset of our clusters. So once we nailed down the redata centering process, it wasn't too bad. You know, that plus using the using of the EBS volumes allowed us to move through that fairly quickly. So, I think he had one. Yeah.
I was going to say, it's like, you're preaching to the choir when you can get the metrics from operations to the developers, because it's like every single performance issue in Cassandra is not, I would say 80% of it is related to your data model and like what you're doing with the
Yeah.
strategies.
Yep.
What would be your top 3 like villains in the scenario where you're like, yep, that's happening again?
My number one villain of that's happening again is misconfiguring speculative execution because I misread where the decimal point should be. And like what would happen is it would like pop up and we're like, oh, we found another one where we didn't fix it. So like that was my pain point. What were some of yours?
Oh God, I'm trying to think.
The thing that you always, I think, complained about to me was probably like everything around backups and like restores and like making, that was the one that was always cropping up as painful until we got really, really solid monitoring there. Like,
Yep, that's true.
That was the area that was just painful because it wasn't as front and center. I think everything else, I think we just ended up with unique problems pretty often. So they didn't repeat except for when I hard-coded something and it propagated throughout 300 microservices.
Yeah, I think probably my big, it's a more generic one, more on on both the operations and the developer side, is really double down on your metrics. In a way, I mean, not besmirching the DataStax Ops Center, but that was a little bit of a blessing in disguise with us moving to Datadog, because we really could double down and pull a lot more metrics in and really tune them to what we needed to see. So
you can put your own data in there as well.
You can, yes.
And it's not just limited to like system JVM,
Right.
system JVM, and everything else.
Right. For instance, we could put in more specific metrics around EBS volumes. The queue, the latency, et cetera.
We weren't clear about this, and we should answer this, and then we should stop because I'm looking at time.
Okay.
When you talk about metrics, we were exporting almost all of the JMX table level metrics into Datadog. So like we would see all of the table level metrics in Datadog in real time along with everything else, which was incredibly useful. All right.
Yeah, that did kind of bail us out a couple times. So
Thank you.
we're done. Okay. Yep. Thanks, guys. I suppose we'll probably turn that off.
So, hello everyone. Thanks for coming in. So I'm Rashmi Krishna SAT. I'm a principal engineer working with Amazon Key Spaces, and joining with me today I have Rohan Gupta, who is the other engineer working with Amazon Key Spaces for Apache Cassandra. And today we'll start with Amazon Key Spaces overview on what it is and how we built it. We'll talk about how we architected it to be highly scalable and highly available as well. And we'll also talk about the features of Amazon Key Spaces, and Rohan here will also be talking in detail about how they were built to provide a seamless experience for the customers. And we'll end the session with some key takeaways and any Q&A that you might have. So Amazon Key Spaces for Apache Cassandra is a scalable, highly available, and fully managed database service. It's Apache Cassandra compatible. That means that you can use your SQL code to manage your tables, create tables, manage tables, read and write data, anything that you can do with a regular Cassandra. You can use your regular drivers, developer tools that you already use. Using Amazon Key Spaces is as simple as changing your Cassandra endpoint to Amazon Key Spaces service endpoint, and it automatically works everything. And you can use your Cassandra migration tools to migrate any data you need to from one place to the Amazon Key Spaces, right? And it is fully managed, which means it doesn't have any servers that you have to manage. No servers. It also doesn't have like any tombstone compaction strategies that you have to manage. It's basically managed by Amazon Key Spaces, meaning by us, behind the scenes for you. And we'll talk about in detail a little bit more about how we'll end up doing that as we talk through the architecture. And serverless also means that you don't have to provision, configure, or operate these large Cassandra clusters. And the tables in this with Cassandra or the Amazon Key Spaces will automatically scale up and down, and depending upon the provision mode or the on-demand capacity mode that you'll end up using, like you can automatically, your tables can scale up and down depending on the load that is coming in. And it's virtually unlimited scale, which means that there is no limit on the size of the table or the number of rows that you have in the table. And at that virtually unlimited size, you still get single-digit millisecond performance, right? And it's highly available, meaning that we provide 5.9 SLA with multi-region replication and 4.9 SLA for single region key spaces table. And it integrates with a lot of other AWS services that we already have today, be it like AWS Identity and Access Management for authentication, KMS for encryption keys, and AWS CloudWatch for providing the data that the metrics, for example, like about if you want to understand how is your key spaces table doing in terms of throttling, metrics, performance, etc. All of that data will be readily available for you to build a dashboard on or anything with the Amazon, AWS CloudWatch system. So thousands of customers across financial sectors, banking, media, entertainment are already using AWS Key Spaces for their Cassandra workloads. And we even have some customers like Intuit who have migrated 100+ terabyte workload to Amazon Key Spaces. So looking back at the architecture, right? Like this, let's say we take through the select query, right? We have the architecture where the client application is talking to Key Spaces. The Key Spaces itself uses the Apache Cassandra's modular architecture, but it is reimagined to provide a fully managed service. So what does that mean? So behind the scenes, when you provide this Key Spaces endpoint, we go ahead and resolve the DNS, and that gives you an endpoint to choose from, right? Like so, which connects to one of the Amazon Key Spaces node. The first thing that we'll end up doing is authenticate and authorize your request. And for this, we integrate with AWS Identity and Access Management, also commonly known as IAM. And with IAM, you actually get a lot of fine-grained access control policies with which you can decide who can or can't access your tables, and you can control it at per operation, like in terms of like select, insert, etc. Right? Once we know the request is secure, at that point we actually go ahead and route this request to the storage partition to fetch that data. And the storage here is built based on the learnings from building other massive large-scale databases which can handle millions of requests too. And we maintain multiple copies of this data so that the requests are, your data is highly durable, highly available, and secure as well. And the storage is also built in such a way that, we take care of this garbage collection, TTL, compaction, etc., that you normally see with Cassandra workloads, right? And we'll talk in a little bit more detail of how is the storage actually partitioned in the next few slides. So that's for the select. What happens with an insert, for example? With an insert, the request is still going through the authentication authorization, then it hits one of the storage partitions, and this storage partition now ensures that it talks to the other storage partitions in the system, right? And by default, Amazon Keyspaces provides you with a local quorum consistency. This means that it ensures that at least 2 of the storage partitions have durably written this data before we acknowledge it back. So zooming out, we have a client application hitting the service endpoint, but we have many service endpoints across different availability zones. We have different key space services nodes, and then we have multiple storage partitions. And like you can see, we show at least 3 availability zones here because we replicate the data at least in 3 availability zones. And we do this so that even if one availability zone is impaired, for example, in this case, AZ2 is impaired, we will re-resolve the DNS to an endpoint which is actually active right now, and then your requests will be flowing through without any interruption. They will just be routed through a different endpoint which is actively working, and you should not be able to see any availability or performance impacts with it. So now that we understand how this request flow works, let's understand how the table data itself is organized. So at a high level, the table is basically made of multiple storage partitions, and it is divided based on the key spaces. Specific parts of the tables are stored in certain storage partitions. And we are cognizant of how much a partition can perform. We limit that to 3,000 RCUs or 1,000 WCUs. And one RCU or read capacity unit is basically capable of providing you up to 4 KB of data. So if you're doing, let's say, a select which is returning you 8 KBs of data, we consume 2 RCUs or tokens behind the scenes. And in case of, let's say this is where the local quorum consistency, but if it's like a local 1 consistency, then we consume half of that because now we can just distribute your request to across all of these storage partitions more equally and use more of our resources. And with a WCU, 1 WCU or write capacity units can provide you up to 1 KB of data read, and by default it is the local quorum consistency. And we limit it to this much because we want that limit on how much in each storage partition can handle, because that way we know we can scale, and we can scale without having a noisy neighbor impact or any other issues that you might land up seeing. So what happens if now customer wants additional throughput? Then we basically land up dynamically increasing the number of partitions so that we get actually double the throughput or double the storage as well. Right? And we do this without the customer really recognizing this. We do this behind the scenes, and customers can provide us hint by increasing their RCU or WCU on the table, and we'll end up increasing there as well. So this works great, but what if there is a skew in this request pattern, right? If it's all uniform, then it scales, it just divides, and you can get double the throughput, for example. In case of a skewed pattern, let's take this example, for partition A. Let's assume that there is a sustained traffic on this partition, let's say row foo and row bar. So now your throughput is also limited. So what we'll end up doing in that particular case is the system is constantly monitoring for such a use case, where if it reaches above a certain utilization, we automatically go and identify, hey, where is this hotness or heat coming from, right? And we go ahead and ensure that we divide or split this partition in such a way that the row foo and row bar are in 2 different partitions, so that you can double your throughput without any issues, right? And this splitting of partitions also help you with storage as well. So that's basically the high-level architecture. Now Rohan will talk us about some of the features that we have today and how we build that, let's say point-in-time recovery and time to leave and all of those features that you'll end up seeing with Cassandra as well.
Hey everyone, my name is Rohan Gupta and I'm a software engineer on the Amazon Keyspaces team. And I'll be today walking you through some of the key features offered by Amazon Keyspaces and how we actually build them. So starting with point-in-time recovery or PITR. So PITR basically helps you to recover your data in case of accidental deletions or updates. And PITR has absolutely no impact on the performance or the scalability or the availability of the data. Yeah, and so with PITR, you can restore your table to any second in time within the past 35 days. And how we do PITR is you can actively select the table or you choose your tables which you want to enable the PITR on. And the pricing is based on the size of the table. And it is it's highly recommended to enable PITR on all your production tables. So how did we actually went and build PITR behind the scenes? So let's dive a bit deeper into the architecture. So as Rashmi mentioned before, a table is comprised of multiple storage partitions. And so let's take an example of a table which has 3 partitions, blue partition, purple partition, and orange partition. So we are building logs for each partition independently, and we are storing them in a S3 bucket. And yeah, so we basically periodically and continuously back up these logs in S3. And in addition to the logs, we are also taking snapshots of the table data from time to time. And we are encrypting these snapshots with the Amazon KMS key or the customer-provided CMK. And so why do we basically take snapshots? So basically, this is an optimization over just storing logs. If we try to build the restored copy of the table just with the logs, it will take us a longer time, and that increases the time to do PITR. So basically, this is an optimization to reduce the total time taken for PITR. And for a given table for each partition, we are storing the logs and snapshots together. So at a particular time, we have multiple snapshots and logs for the table in S3. Now let's say you as a customer, you delete some of your data that you didn't intend to, or you do some updates that was not supposed to do. So Keyspaces makes it really simple and easy to recover your data to a previous good state. To do that, basically, we take a restore time from the customer, and we first validate that it is a valid restore time. It is in the past 35 days. And once that is validated, we go further, and we go into the S3, and we look for the snapshot, which has the most recent version of your data. Once we get the snapshot, we take the restore time and the snapshot time, and we get the logs between those. And we apply forward any changes that happen to the snapshot. And yeah, so we do this process continuously for all the partitions, which basically results into the whole restored table. Now, moving on to another feature, which is time to live, or we call it TTL. With TTL, you can basically insert a row or a cell with the TTL value, which is in seconds, and basically the row disappears after that certain seconds. So queries don't return expired rows or cells. And records are removed from the storage by a background compaction process, and which is typically within 10 days. And this does not have any impact on the performance or availability of the table as well, because this process is completely asynchronous, and this runs as a background process. So how do we actually do the compaction in background? Let's dive a bit deeper into this. So we have a fleet of hosts for this particular use case. And we already mentioned that we continuously take the snapshots of the table and store in S3 to do PITR. And we use the same snapshots to do the TTL compactions as well. And why do we use the snapshot? If we directly go and do a read on a table, that will be a very costly operation for both us and the customer. So instead, we use the snapshots instead to do the use case. So basically, a TTL host go to the S3. It gets the partition, the most latest snapshots. It then compacts the snapshot. It basically removes the expired cells and rows. And it then writes back to the storage partitions. And all this happens in the background. So it does not have any performance impact. Now let's see another feature which we recently launched, multi-region replication. Multi-region replication helps you to get a fully managed active-to-active replication across all AWS regions, which helps customer to basically build globally distributed applications. And you can read and write data to any region across the globe. And the replication lag within regions is typically within a second. So how does multi-region replication actually work? First, the application writes data into the table in a given region. Then the data is successfully written in that particular local region across 3 AZs. And then we send a success back. And finally, that data, we have a replication service, which basically send the log records across the other regions configured in the multi-region key space. And the other region basically accepts those inserts. And this step happens asynchronously in key spaces. What about handling conflicts? Like in key spaces architecture, we don't have a leader. So all nodes can have inserts at the same time. How do we handle conflicts for the same keys? So in key spaces, the last writer wins. We use that method of data reconciliation. And all regions agree to the latest update based on the cell level timestamp. But there can be cases that the timestamps are equal. In that case, we go with the larger value of the data type, of the cell, basically. So we have a strict ordering. We do a strict ordering of the data type, and we then select the largest value out of those. So for example, if it's a string, we take the lexicographically larger string. So Jello will be greater than hello. So Jello will be accepted. In case of integers, the larger integer. And in case of collections, we do a canonical ordering of the data type, and we figure out the bigger out of the collection. Yeah, so basically all nodes across follow, in key spaces, across all the regions, follow the same data reconciliation process, which makes this whole process more deterministic. And this basically results into the same image of the item across all regions. And any conflicts or divergence in key spaces is automatically handled. So moving on to some of the key takeaways, Amazon key spaces is serverless, which means customers don't have to provision, patch, or manage any servers. They don't have to install, maintain, or operate any kind of software. Customers don't have to worry about configuring other processes like compaction strategies, managing tombstones, JVMs, garbage collections, etc. Table is made of multiple storage partitions, which are spread across multiple servers, across regions, across availability zones in a region. And we offer high traffic isolation and partition splits for better throughput and more storage. And there's virtually unlimited storage and throughput for a table. And finally, we're fully managed with a per table granularity. Many of our features work at a per table level, like Pitter and like TTL. And they do not impact, enabling them do not impact the performance or the availability of the table. We have some other sessions going on in the summit. You should attend, they're quite informative. And we have a workshop also going on that's tomorrow, 11:50, which you can attend, and we have a dinner reception. And if you have any detailed question, we also have a booth where you can drop by and we can answer any of your questions. And yeah, and we're open to any questions. Yep, please go ahead.
partition? Like, is it a one-to-one, or it seems like it's like one to many? And how does that maintain? You know, lots of storage partitions map back to a single Cassandra partition.
So behind the scenes, right, like, so at the end of the day, what you're looking at is for a given key, right, like, so Cassandra is also like basically a key value lookup. So for a given key, it's basically we calculate what we call it as like hash of that key. And based on that hash of that key, we go and figure out like, you know, which is the right partition to actually store or route this request to. And this is where the one thing that we didn't talk about in these slides is like, you know, we also have another thing like metadata systems which actually provide you that data. So let's say if the storage partitions basically become bigger or larger, if we have to split, then that is basically pushed back through metadata systems. We get hint back directly from storage partitions to the key spaces nodes or through metadata systems. We get that hint back now saying that like, you know, hey, this data is now split, so these are the new partitions now. So this is where you need to route your next request to. And this is basically an atomic operation when the split happens. It's like, you know, we have 3 nodes and then like it becomes kind of like a 6-node cluster where it now becomes like 2 child partitions. And that process is basically atomic, so that there's only one, at any point in time, there's only one partition which is taking that request.
How does that compare to AstroDB from a performance perspective, from a cost perspective? Do you have any details on that?
I think, I mean, we have some data on like how key spaces performs in terms of like single-digit millisecond performance, etc. And if you're looking for exact benchmark, maybe you can come by the booth and like we can talk in more detail about like exactly what type of performance you're looking at. Like, you know, is it availability? Is it latencies? Is it the cost performance that you're looking at? So there is like usually various factors that come into picture when you're looking at a specific performance. Sure. Go ahead, yeah.
How do you handle moving between regions? So let's say that I have a global Cassandra key space in, say, US East 1 in the EU, and I want to expand out to AP. But I don't want AP to start taking traffic until all of the data and stuff is replicated over there. So
I could actually take that one. Currently, we don't support adding replication regions to a multi-region key space, but we support creating new tables or new key spaces, net new. Yeah. So currently, we cannot support that feature as of now. But you can. We have certain timelines. I think you can come to our booth, and the product team can help you with that.
Sure. Go ahead.
So my question is that knowing the fact that Cassandra 5 will be released later this year, do you guys have any plans in your backlog to support Cassandra 5 features?
The Cassandra features versus the Amazon Key Spaces features exactly don't work in a similar fashion in terms of like the version deprecations or that you see with 3.11x and everything. But that being said, like, you know, we do have like a feature roadmap to keep it, you know, to support more and more of those features that you also see with Cassandra 5 or other things. But yeah, if there is a specific feature that you're interested in, like we could definitely work with our product team here. Like, I mean, we have Meet here, like who can help you with like trying to understand like you know what feature you're interested in and like where in our roadmap does that align to. Sure. I think.
You guys mentioned a little bit about performance earlier. Are you guys able to offer any performance SLAs for reads and writes?
And when you say performance, are you talking about the price per?
Latency.
Got it. Currently, we don't provide any SLAs for latencies. What we kind of promise is like single-digit millisecond latencies at any kind of scale that you want, but we don't provide a specific SLA. You had a question?
Yeah. How detailed are your metrics? I.e., if I'm running some new queries through there, do I have the ability to drill down and see how that's performing?
You want to take that or?
emit. We integrate with like Amazon CloudWatch. So you can go and you can tune, you can see your metrics for inserts or, yeah. So you can basically monitor your latencies using CloudWatch.
So usually there are kind of different classes of metrics. Like let's say if you're looking at performance, you can look at your latencies per operation, per table that you have. Like we also put in like, throttles, for example. We kind of also show you capacity utilization metrics. Like for example, like what is your provision capacity, consume capacity, those kind of things as well. So there is usually an array of different types of metrics.
Has the APM tool where you can see which actual queries are taking the longest time. Is that similar thing available in CloudWatch for Amazon Key Spaces?
Kind of, yes. So if you're looking for specific operation level, like specific key, like specific things, like, I mean, you could, like what the service level things that you kind of see in the CloudWatch is like aggregated at the operation and at the table level. Like if you want more detailed metrics, like if you're debugging something, for example, like one of the things that you can also do is like integrate with other systems like AWS X-Ray, for example, to get those detailed metrics of like, hey, what is my queries, how long did it take, like at your client level as well.
And also to add that, we also have CloudTrail integration for DDL operations. So that also gives you an insight.
Yeah, especially if you want to audit like the writes that is going on in your systems. So, yeah.
Do you guys provide any search capabilities on top of key spaces? I know that in Astra there was Elasticsearch or Lucene on top that clients can use. Is there anything like that in key spaces?
No, not right now. I mean, are you kind of curious about like a text search, like vector search? I'm just curious about like your use case. Got it. No, right now we don't provide that. I mean, it's basically still a key value lookup, but yeah.
I think, yeah. Thank you. Thank you for coming.
Thank you.